Okay, it seems that most people are finding their way to the right link. Apologies for that. No idea what happened, to be honest. Especially since it seemed to expire yesterday when I didn't have a session at all. So that is bizarre, but okay. Don't know what I did wrong. Give it a few more minutes and then get started. All right, so I'll check my mail again and then, okay, no new. So probably everyone who intended to be here is here. So let's get started. Okay. So the first thing I'm going to do is to share my screen. And show you some slides. Not everything will be slides, of course. I'll also be doing things interactively, but the slides are kind of the backbone, so it's always easier to use those to get the show on the road. All right, so Scientific Python. One of the things I would like to mention up front, of course, as usual, for those who are familiar with the training format, please ask questions. You can ask questions via the chat. If things are a bit too elaborate to type in the chat, you can activate your microphone and just ask the question. That's not a problem either. But the more interactive this is, the more pleasant it is for all of us, including me. So feel free to ask questions at any point. I might not be dealing with them really immediately, because it might be that I'm planning to do so on the next slide or something like that. But I'll always keep an eye on the chat. Okay, let's get started. So this is a link and a QR code which I use in face-to-face meetings, but I'll paste the link in the chat. There you go. And basically what that links you to is this web page. That gives you some idea about the content of this particular training. And more importantly, it also has a link up here to the GitHub repository for this particular training. And that's here. You find quite a number of things there. One of the things is the slides I'm going to use. Those are here. But perhaps more interesting, there is also source code, the source code directory. And that directory contains quite a lot of material that we will be dealing with today, but also a number of extra things. So it's definitely worth to have a look if you're interested. Another thing which it contains, and that's also useful, that is the environment YAML file to recreate an environment that is suitable to run the example code and so on. So that gives you access to the environment. It's Conda based, so you can initiate it with either Conda or Mamba, whatever you're most familiar with. Okay, let's get back to the slides. So, of course, feel free to follow us on LinkedIn. There is always information about HPC in general, about the VSC in particular, Vlaams Supercomputing Center, and obviously also about our trainings and trainings provided by well, our colleagues abroad or in the Walloon region. Okay, a few typographical conventions used in these slides. Shell commands, but I don't think there are many left, are rendered on a black background. So basically that's your typical bash shell in which you can run just Python scripts or whatever you do on a shell. And of course, as usual, the $sign just represents the prompt. You don't type that. Python shell commands, I don't think there are any left at all. Don't remember, but I don't think so. So basically this is just the Python interpreter, or the IPython interpreter is rendered like this. But I don't think there's any left. I should actually look at the slides and maybe even remove this slide. This is still very relevant though. We have inline code fragments are rendered in this monospaced font, just to make them stand out with respect to the running text. And longer code fragments are similar font, but on a grayish background. Data files on a greenish, yellowish, whatever color this is, background, so to make them a little bit distinct from source code. And what you will see on a regular basis is these ellipses here. And although ellipsis is a thing in Python, in this case it just means, okay, not enough space on the slide, either see the previous slide, the next slide, or the provided source code, because it's all there. But that's just to save some space. Okay, let's start with a little motivation. So one of the things, of course, which is quite important in scientific programming is your libraries, and that's what we're mostly going to talk about today. I'm assuming that you're sufficiently familiar with the core Python language and the standard library of Python, so we're not going to talk about that. We're going to talk about third-party libraries which are useful for scientific computing. But perhaps let me first start with a little poll, because I regularly make references to other stuff, and that other stuff is programming languages, and hence it's useful for me to know a little bit about your background, so that I can give relevant examples. So the question is, what is your primary programming language? And by that I mean the one which you use most often. That might be Python, who knows? That could be MATLAB. That could be who knows? That could also be. I only have 5 options, so now I'm going to lump them together. The classic programming language, the trinity of HPC. So let's have a look what your background is. Python, Python, Python. A little bit of R, a little bit of MATLAB, a little bit of C, C++, Fortran, but mostly Python and Loop. Okay, there seems to be a question somewhere. Or if someone is raising his hand, probably. Okay. Which I don't see. Question the tab. Let's have a look. Oh yeah, no problem. Don't worry. It's not that important. We don't need exact numbers. It's just to have an idea about the rough proportion of people who are what you are using. That's also, it's not exactly science here, so it doesn't matter. Okay, so mostly Python, MATLAB, a little bit of R, and a little bit of C, C++, and so on. Okay, that's good to know. All right, let's start with a little motivation. So, out of the box, actually, Python is pretty slow. One of the reasons is that Python is an interpreted language, and yeah, it makes Python really, really slow. So things will improve a little bit with the release of Python 3.12 because some optimizations have been done and Python got a bit faster, but it's not as if it's on par with programming languages such as C++ or Fortran, not at all. So basically, that is an issue. So of course, that's not necessarily a problem in the sense that it's quite okay for what I would call a one-off. That's a program which you run only once or just a few times. Then yeah, okay, you don't really care that much. It's also okay for prototyping, of course, because for that Python is a very nice language in the sense that you can write programs pretty fast. So your time as a programmer is also valuable if you are very productive in Python. And then, of course, it's a good programming language to do prototypes. Also for programs that run just a very short time, like sub-second or even a couple of seconds, yeah, who cares? I mean, you kind of have to make an estimate whether you will have return on investment of, let's say, making things fast. If there is no return on investment, don't bother. I mean, it's not for the sport of it. So for some people, yes, but typically you have better things to do. But what pure Python is definitely not okay for is computational intensive tasks, because out of the box for that, it's really too slow. And I'll motivate that with numbers. Let's have a look at this particular code. So I'm doing two things. I've got two functions. The first one is going to initialize a matrix, and it is just doing that by drawing numbers from a random distribution. Whatever, it will be an n by n matrix, nothing special. The second function does a matrix multiplication. And as you can see from the implementation, we have the typical nested triple for loop. And of course, the work is being done in the inner loop, which ranges over k. And it's just a classic implementation. So nothing out of the ordinary here. You're all familiar with that from your classes in mathematics. Okay, let's time that for 500 by 500 matrices. So yeah, that's a number of elements, but not that impressive. And the initialization, so the init matrix function, takes 1/10 of a second approximately, while the matrix multiplication takes 32 seconds. Now, what's your gut feeling with respect to this 32 seconds? Is this fast? Is this slow? What do you think? How would you describe this? Any opinions? Slow. I would agree. It's quite slow. And we can actually quantify that by writing a C application, which does the same thing. And if we time that, you see that the initialization indeed is a lot faster by a factor of 8, probably, or 7 at least. Okay, I don't care that much, but the matrix multiplication is rather spectacularly faster because it only takes half a second. Okay, so the question is, why is Python this slow? Okay, we can argue that indeed it's an interpreted language and so forth, which is true, but maybe there's another reason. Any suggestions what is going on here? Why this is so slow compared to C? Well, of course, I've been slightly deceiving you just by using certain terminology. And that puts you, let's say, in a certain frame of mind, which actually helps me make my point. So what I've been telling you is that I have been creating a matrix. Yes, but okay, how do we view a matrix mathematically? Well, mathematically, we view this as something where all the elements have the same type. Now, the data type I've been using for this particular implementation is a list of lists. That's not really a matrix. Why? Because in a list in Python, I can store whatever I want. The first element can be a string. The second element can be a list. The third element can be a floating point value, whatever. I can choose. Python doesn't mind. But yeah, at the end of the day, that is going to be somewhat problematic. Let's go to the core of this matrix multiplication. So the last line on the slide. And that says, well, okay, what do we need to do? We have A. A is a list. No, let's rephrase that. We have A, and we apply the indexing operator, so the square brackets. Can we do that? Okay, we have to check. Yes, A is a list. That's good. Okay, now I'm indexing with I. Can I use I to index a list? Yeah, it's an integer. Okay, is it a valid index? So is it between the length of the list minus 1 and minus the length of the list? Yeah, it is. Okay, that's great. So I can fetch whatever is in AI, and I'm going to apply the index operator. Again, the square brackets. Can I do that? Yes, because AI happens to be a list. Okay, I need to check whether k is a valid index, blah, blah, blah. We already did that. And finally, I get the value of aik. Okay, great. Now, I have to do the same shenanigans for b. Okay, and then I have to check whether I can multiply aik and bki. Yes, I can, because both are float. Then I have to do the whole thing again for c, because I want cij. I need to check whether, after checking whether it's a list, whether it can be indexed, whether that can be indexed, blah, 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 I need to add a number to the result. Can I do that? Yes, because Cij also happens to be a floating point value. So as you can see, I need to do quite a lot of type checking, and I need to do that because in Python, a list can contain anything. So I need to check. That takes a lot of time. Well, I don't need to check, the Python interpreter needs to check, and that takes a lot of time. So basically, it's not as such because Python is a slow language, but rather because I'm using the wrong data type. Representing a matrix as a list of lists is not really such a brilliant idea. So that's what's actually going wrong here. You can do the same thing also in Fortran, and then you see that that is even faster. So basically, for Fortran, you see that we get to a little bit more than 1/10 of a second for the matrix multiplication. Okay, so this quantifies speed a little bit. Of course, this is naive. Don't do this. Bad idea. Don't write your own matrix multiplication. That is not a good idea. So we have quite a number of libraries for numerical computations, and one of them is in fact NumPy. And one of the data types which we have is a representation for arrays, which in fact is pretty optimized. Also, we have a lot of matrix operations as they are in the BLAS library. BLAS stands for basic linear algebra subprograms. That's an old library which is everywhere at the core of any matrix operations which you might want to do on a computer, and which you don't implement yourself. Typically, you use the BLAS library somewhere. Also other linear algebra operations, but not that many. Fast Fourier transforms in there, mathematical functions defined on arrays, as we will see, pseudo-random number generation to initialize arrays, simple statistics, etc., etc. So all of that is in NumPy. And it might be a good idea to use that and to see how that speeds up our particular task here. So there are other libraries, and we will deal with others as well later on. So if we do the same thing in NumPy, we can actually initialize our matrix with NumPy random uniform. As you can guess, I'm going to sample from a uniform distribution between 0 and 1. And the shape of the array on which I will obtain is n by n. So it's going to be a two-dimensional array with n rows and columns. Okay. Notice we have import numpy snp. This is just an alias for the numpy module, and that is the usual way of using NumPy. Okay, the matrix multiplication is even simpler because we can use the add operator, which is part of the Python core language. Okay, so if we time that for our 500 by 500 matrix, this is actually not too bad because for the matrix multiplication, as you can see, we went down to below 1/10 of a second. So now we're even faster than Fortran. So that's kind of cool. Okay, so that looks much better. Bottom line, use the right libraries and you will improve your performance significantly. And that significant is illustrated by the table here. We started off with pure Python list of lists for matrices at 32 seconds. C did half a second, Fortran did 1/10 of a second. Python using NumPy less than 1/10 of a second. And of course, the actual winner is Fortran in combination with the basic linear algebra subprograms library. And that goes down a little bit with respect to Python as well. I like Fortran, so it just has to win here. So why is NumPy that fast? Because under the hood, it's also going to use that same BLAS library, which I called from my from my Fortran implementation. So bottom line, pick your data structures correctly, and also, of course, rely on libraries which provide you performance. And for linear algebra, for matrix operations, NumPy is definitely the way to go. Okay, there are performance pitfalls, but okay. So, in summary, you actually gain a factor of 415, and that's of course pretty huge. It's 2 orders of magnitude, and that is not really to be sneezed at. It basically means that your original program was 415 times slower. So suppose it originally took your optimized version takes a day. That means that the original would have taken more than a year, which is kind of prohibitive to do your computations. So this is a deal maker / deal breaker. It's quite important. Okay, so NumPy, how do we create arrays? Let's perhaps do that interactively because it's always a little bit nicer to do that. So I have a Jupyter notebook open. It lives in my environment, and that has Jupyter Lab. So I'm going to open this, create a little bit more screen real estate. And of course, if I want to use NumPy, the first thing I'm going to do is import NumPy SN. What you sometimes see, and what I would really discourage you to do, is something like this. So from NumPy, import star. Don't do this, bad practice, very bad idea. Always do explicit import or use np as a namespace prefix. because otherwise you pollute your namespace and you've no clue what is in there. You're going to redefine important functions, things are going to go wrong, so don't do that. Okay, let's create a couple of matrices or a couple of arrays. So for instance, I can simply create an array, a one-dimensional array, let's call it V, and I can do that using the array function. And then I can just provide a list of numbers, let's say 3.0, 5.1, and 7.2. Okay, so this is a one-dimensional array, and if I just render that in Jupyter Notebook, you see I get this representation. So that's pretty straightforward. If I want a two-dimensional array, same thing. And you can already guess, you just use a list of lists in order to represent the rows of your array. So let's say 3.1, 5.3, and okay, let's not make it square. 7.4, second row, I don't know, -1.3, 5.5, and -5. Okay, so that's it. And now I've got my array, and as you can see, it also gets nicely rendered as if it were a matrix with 2 rows and 3 columns. So this is the very easy way to make small arrays, and of course there are different ways of doing that. For instance, I could have an array v1 which consists entirely of zeros. I have to specify the shape of that array, and that always has to be a tuple. So if I want a one-dimensional array, I have to specify a one tuple. For instance, I want 10 components, and this is what I get. And of course, as you can guess, I can do np once. Let's make that an array of length 5. Very easy. So don't forget to specify the size of a one-dimensional vector. You need a one tuple, so a tuple with one element. How do you create that? Easy. You just have the round brackets, which you always use for tuple, no problem. And it has a single component and the trailing comma. Don't forget the trailing comma, because this would not work. So if I do np once, 5, that also works. Oh, this is cool. That's nice. I didn't realize that would work. Okay, great. Good improvement. Anyway, so I can also create, for instance, a square matrix. Zeros. And for instance, a 4x4. And as you can see, that's what I get. Okay, so yeah, I'm not sure that I can do much about that, about the keyboard. It's a somewhat silent keyboard. I used to have a mechanical one. Then you should have followed my sessions. That was distracting. Can I somehow lift the microphone? Let me think. Then I need something to put it on. And I can likely put it on my speaker. Okay, so with some luck, this is a little better. I'll also tilt it a little more upward and hope that it doesn't pick up that much noise from my keyboard. Okay. All right, let's go to the slides to see whether I forgot anything. No, not really. So what I didn't mention is the empty, and that's an important one as well, but I'll come back to that later. So basically it gives you storage space, but no initialized values. Perhaps let me show you. So if I do np empty, and I want a 5 by 5. Yeah, closing one more bracket is actually a good idea. Then you see that you get all kinds of strange values. So basically, this is intended to make sure that you have sufficient space to store a 5 by 5 array, but it's not been initialized. So that's basically the idea. And this is kind of important, but I'll explain later why. Okay, so two-dimensional things. Yes. So if you want an identity matrix, you can actually just do NPI. It's usually indicated with a capital letter I, the identity matrix, and hence the I function. Okay, so that's kind of easy. Now, the default type is in fact double. Let's have a look. So I can ask for the D type of this function, and that is the type of the elements. And then you see that indeed I get float 64. So that is 64 bits, which means 8 bytes, which is double precision. We'll talk about the types in detail later on. So typically, when I get such a matrix and I don't specify anything special, I'll typically get double precision. So besides the type, I also do it for A. So each such array has an A type attribute. I also have the shape, and the number of rows and the number of columns. If I do that for V, see that you get. Okay, so that's all straightforward. You've already seen the random initialization. So basically there is a module called random in NumPy, and that has quite a number of distributions. Among them, of course, the uniform distribution, the exponential distribution, the Gaussian distribution, which actually is the normal distribution, etc., etc. So we have quite a lot of those distributions. We can have a quick look. As you can see, beta, binomial, chi-square, Dirichlet distribution, whatever, gamma, which we'll encounter later, and quite a lot which I have no idea about. I have no clue what a Gumbel distribution is. Anyway, normal distribution is also somewhere here. Yeah, here it is. So basically, there is quite a lot of different distributions which are available in the random module. Okay, and as I mentioned, you have to specify the shape as a tuple here. Okay, NP array I already showed you, and what you can also do is read an array from a text, and a function which I rather like for that is gen from text. It just takes a file name as an argument, and it supposes that your array is encoded as rows on a line, separated by spaces, and one line per row. You can fiddle with this. You can specify the separator that separates elements in a line, and you can also fiddle with the separator which separates rows as well. So that's optional arguments for gen from text. You can also specify the type which you wanted to have, etc., etc. So there are many options there. Okay, so yet another way, and let's again, I'm just going to show it. So there are a couple of ways to generate, let's say, special arrays in the sense that they have, for instance, equidistant elements, and you have essentially two choices there. We can use a range, and that has the same semantics as range in Python. So it takes the starting value and it takes an ending value, and then it also takes a number. Then it also takes the increment. So, for instance, not 0 in this case. And then you see that it's the same semantics as in range, because the last value is actually not included. So the last value which we get as output is 0.9, because if we add the increment 0.1, we end up with 1. And so, of course, 1 is not less than 1, and last element is going to be 0.9. Okay. This is, of course, a little problematic. Any idea why this could lead to trouble? Everything remains on a single row. Yeah, but if you like, I can actually make sure that you get something two-dimensional. Now I have to be a little careful. This is 10 elements, I think, so I can reshape this if you like to, let's say, 2 by 5 or 2 by -1, just for convenience, and then I have a two-dimensional array. So that's not a problem. For a new row, this I don't quite get. But probably you mean the reshape kind of thing, which I'm doing here. But I'll return to reshape later. So no, there is no, actually there is, as far as I'm aware, there is no size argument to a range, unless it was added at some point and I didn't notice, but we can always check. So no, there is no such argument. But the point, the troublesome point is basically that this is floating point. Floating point is subject to round-off errors. So basically that means that I, due to round-off, can end up with one more element or one less element than I'm actually expecting. And then, of course, if this happens in a program where you, for instance, add 2 vectors or something like that, then they might end up accidentally, just due to round off, with a different number of elements. And that is a little annoying. So there's an alternative, which you might also know from MATLAB, and that's linspace. That allows me to specify the first value, the last value, and the number of elements which I want. So this will have 10 elements for sure, and its first will be 0, its last will be 1. And then you see that indeed I get 10 values evenly spaced between 0 and 1. And besides linspace, there's also logspace, which allows you to create, well, numbers which are, let's say, in order of magnitude spaced between them. So that's also convenient. So the usual caveats in scientific computing apply. You have to be really, really very aware that floating point arithmetic is not associative, not necessarily commutative. So basically, you can get different results depending on how you order your elementary operations. And of course, you have only a finite representation, 64 bits, of something that is in fact infinite, a real number. So yeah, it just can't work. I mean, you will get into trouble at some point with round-off. That's a given. Okay, so in general, it's good practice to actually use linspace rather than a range. I will be using a range from time to time because, of course, it's pretty innocent when you have not that many elements. It gets more tedious when you have many elements in your array which you're generating. Okay, so let's talk a little bit about data types. I already mentioned that by default, you typically, and I'll show you a counterexample after I've talked about this slide, you typically get 64 bits floating point values by default. But of course, there are other data types. And for integers, for instance, we have quite a lot. In Python, you just got the type int, that's it. And in Python 3, you know that an integer, in fact, can have any size. You can just keep on adding to it, no problem. Now, of course, that is slowish. So that's not what most other programming languages do. And that's also not what NumPy does. NumPy says, well, okay, I'll give you a couple of implementations of integers, all with different sizes, and you pick the one which is most appropriate for your problem. So we have NP int 8, int 16, int 32, and int 64. And the number is the number of bits for that integer. So an NP int 8 uses 8 bits to represent an integer. So that means an integer from minus 128 up to 127, sorry. For instance, an int 32 means minus 2 to the power 31 to 2 to the power 31 minus 1, and similar for the other types. So basically that means if you have only small integers, you can use NP int 8. Question is, why would you do that? Why would you want to use an int 8? I mean, you can store it in int 32 or in int 64, so why bother with int 8? Yep, saving memory. And that's of course important because sometimes you're dealing with large data sets, and an int 8 is 4 times smaller than an int 32. It's 8 times smaller than an int 64. So if you have lots of them and they don't exceed 127, why would you sacrifice 8 times more memory to store the same data? Bad idea. So that's why they're there. Also, there is what you can store in RAM, but there is another very important consideration when you're doing scientific computing. One of the things that makes your code slow is in fact not so much what you might expect. Well, at the end of the day, it's of course what you expect, the number of computations you can do per unit of time. But there is another thing as well, and that's how fast can you get data from the memory of your computer to the CPU where the actual computations are being done. That's your memory bandwidth. That's the number of bytes you can transport per unit of time. And that is, in fact, usually the restricting factor with respect to performance. So it's not so much computations on sich, but rather the bandwidth, so the amount of data which you can grab in order to do your computations per unit of time. And then, of course, that means that if you have a given bandwidth, and yes, that is a given on particular hardware, then of course it means that if I can store 8 times more values if they're encoded as int 8 than I can do if they're encoded in int 64. So not only do I save memory, but I also use my bandwidth, my available bandwidth, more effectively. And that's perhaps, with respect to performance, even more important than whatever is stored in memory. Okay. So for integers, we also have the unsigned versions. So we have an NP uint 8, uint 16, uint 32, and uint 64. And that basically means that you can store, for instance, for uint 8, you can store numbers between 0 and 255. So that's the unsigned integers. For int 32, you can store numbers between 0 and 2 to the power 32 minus 1, which is around, well, a little over 4 billion. Okay, so that's our first type. The second type is floating point numbers. And in Python, we've got one type which is float, and that is in fact float 64. So float 64 is what you are computing with when you just use Python. In NumPy, we actually have 4 floating point types with float 16, 32, 64, and 128. So float 64 is double precision, and that gives you 15 significant digits and numbers up to 10 to the power 308. The smallest non-zero value which you can represent is 10 to the power minus 308. Okay, so that's quite a good range. There's also single precision, so float 32, that gives you 6 to 7 significant digits, depending on how you count. Typically, you get 7, and 10 to the power 38 as the largest number which you can store. And there is also float 16, and that gives you 4 digits of precision. And there is also float 128, which gives you 31 digits of precision. Okay, so that's good. Again, of course, the same reasoning applies. Depending on how large your data is, you pick a certain data type. Depending on how much precision you need, you pick a certain data type. That conserves memory. That's good for memory bandwidth. Okay, but, and that in fact also applies for certain integer operations, it goes a bit further, because you might have heard of factorization. So basically that means that the same arithmetic instruction is carried out on multiple numbers at the same time. And of course, a vector width is again fixed and given by the hardware you're running on. So if I'm doing a computation in a loop on an array, then I can, in fact, depending on the hardware, doing 4 double precision floating point operations at the same time, or 8 single precision operations at the same time. Ah, interesting. So not only is my bandwidth going up, but also the number of operations I can do in one clock cycle. So that's actually pretty cute. So if you don't need precision, it's much better to use float 32, because that means that your code will execute quite a lot faster. Not entirely a factor of 2, but theoretically up to a factor of 2. Okay, then you might say, yeah, that's nice, but I really need very little precision, so I'm going to use float 16. Yeah, problem is there is no hardware support in modern CPUs, well, in current CPUs, for float 16. And the same applies to float 128. So that is emulated. And although you might expect that float 16 is faster, because you can do more at the same time, no, the hardware is not supporting it. So that means it's emulated. It will be actually slower on CPUs than float 32. There are 2 things going on. One thing is that Intel, for instance, will be adding float 16 support to its future generation of CPUs. That's one thing. And of course, NumPy is ready to interact with stuff that lives on a GPU. And on a GPU, on modern GPUs, float 16 is a thing. And you can actually do very fast computations on GPUs using float 16. That's why it's there. Float 128 I would avoid if I were you, because also there is no hardware support for that, and it will slow down your computations considerably. So the default is going to be float 64. I forgot to mention the default for integers. So for integers, it depends. On a 32-bit platform, an int will be 32 bits. On a 64-bit platform, you will actually get NP int 64 as default. So that means that if you really want to make sure that your code is portable across all platforms, it's not a bad idea to explicitly specify whether you want int 32 or int 64. For floating point, it doesn't matter. It's always, the default is always float 64. So if that's what you want, you're good. Okay, and by the way, interestingly, Windows has been sort of 64 bits for quite a while. On the other hand, if you check in a notebook running on Windows, well, you might still get int32 as a default. So that's a little bit weird, but that at least used to happen with Anaconda last time I checked, which is now more than a year ago. Okay, we also have complex numbers. Of course, we have them in Python as well, and in Python there would be double precision. So we have three complex types in NumPy, complex 64, 128, and 256. And this might be a little confusing, but 64 here means that there are 32 bits for the real part, 32 bits for the imaginary part. So that's single precision. And the NP complex 128 is your double precision. So don't get confused there, because otherwise you're computing in the wrong precision. And there are also Boolean values, NP bool, but they take 8 bits. So don't be tempted and think that it will be 1 bit per Boolean value. No, it's actually 8 bits. And yeah, that's not so exceptional, because that's frankly the case for most programming languages. Also for C++, for instance, that would be the case. And then you can also store characters in arrays. Of course, what you need to realize is that when you think of a string, and especially in Python, that is something that has arbitrary length. Of course, here you're dealing with an array. So if each row in an array represents a string, that means that all your strings have equal length. That's pretty obvious. So we don't really have strings, we have character arrays. Okay, if you want to specify a certain type, almost all functions which you have to create new arrays take a dtype argument, and then you can specify the type you want. For instance, what we can do is say, well, okay, I want an NP of zeros, and I want 5 of them, and the dtype should be NP int. Okay, and something horrible happens. What did I do? Well, that's impressive. Okay, it gives a warning. Oh, that's very nice. Okay. So actually it says don't do this, you are stupid. So let me make that into 32. So one of the things you might notice is there is a subtle difference here. And I'm going to do the NP0 thing again, just so that you can compare easily. The one thing you visually get, besides that the dtype is explicitly mentioned here, is that you get the dot here. So this is an array of floating point values, this is a value of an array of integers. And you can notice that immediately because there is a dot, a decimal dot for the floating point. So that is actually just a visual reminder that that is an integer array. So one of the traps, one of the things I said was, well, yeah, by default you get a floating point array. Yes, but do you? Mostly yes, but let's take a range. And now my starting value is 0, my ending value is 5, and I have an increment of 1. And NumPy has not. Yeah, if I use a single R, that would be so much better. And then you see that you actually get an integer array. And if you don't believe me, I'll show you. Because the deep type of that thing is int64. So this is something that might surprise you or not, but at least it's what's happening. So whether it surprises you or not is not so much my concern. The point is that you need to know, because it means that you can inadvertently create an array of integers. And then you start computing with it, and you, for instance, multiply that with an array of floating point values. Okay, that means that your integers are going to be converted to floating point first, and that's going to eat performance. That's not what you want. So be careful if you create arrays that you really create them in the right type. So what I typically do, and that goes for any programming language I'm working in, if I intend a constant to be a double precision value, I'll always put dot zero at the end of the value. So what I would normally do, I would say, okay, this is 0, 5, and 1. And then I can't make that mistake inadvertently. As you can see, now I get a double precision array. So that's something to keep in mind, that although it's true that most array creation functions will return dtype np float 64, that's always quite true. Multiplication between integer and floating point number. Yes, so basically if I, also in Python, it doesn't matter whether this is Python or NumPy, if I type something like 3 times 5.1, okay, 3 is an integer, 5.1 is a floating point value. So what typically happens is that all the types in an arithmetic expression get promoted to the largest type. So the largest type in this case is floating point. So my integer 3 is going to be converted into a floating point value, and then the operation, the multiplication, is carried out. So that is what always happens. That happens in Python, that happens in C++, that happens in anything. You always get promotion to the largest type. That happens under the hood. I mean, whether I write this or I write that, I get the same result. That's not the issue. But performance-wise, cell 26 executes a little slower than 28. Because in cell 27, first, my integer 3 needs to be converted to a float 3.0. While in cell 28, I start off with 3.0. So mixing types in arithmetic expressions is a bad idea and will cost you some performance. Not that much, of course, but yeah, there always is a little catch. And of course, if I'm just multiplying two numbers, who cares? But if this is in a for loop and I'm doing this a million times, well, okay, I don't think so. I'd prefer to actually have them to be the right types without conversion each and every time. So that's a not unimportant performance consideration, which is not specific to NumPy, which is not specific to Python, but which goes for any programming language, because to my knowledge, they all do the same thing here. Okay. So that's something to keep in mind. How do you access elements of an array? Yeah, well, that is pretty straightforward. I've got my A, I'm going to display it again, and I can use the indexing operator, so the square brackets, in order to get my elements. And of course, in Python, this is important for MATLAB and for R people, array indices start at 0. So if I want the first row and the first column element of my matrix, I would have to use 0 and 0. First row is 0, second row, first column is 0. So if I want second row, second column, I'd use A1, 1. So this is of course an important difference between MATLAB, R, Fortran, and Python, C, C++, then basically indexing starts at 0. So that means if you're translating algorithms from MATLAB to Python or from R to Python, keep this in mind. Otherwise, you will get interesting errors. Also remember for those people that in fact indices can be negative in Python. So if I want the last element of the first row, I can just type 0. That's my first row. And the last element is at index -1. This works in Python. It's not an error, it's a feature. So basically, this is something that's very important to realize for MATLAB and R people. You can have negative indices in Python. It works, and it's actually a very nice thing to have because it simplifies certain code quite a lot. But it's something to keep in mind, because if you're computing indices and you make a mistake and by accident you have a negative integer, -1 or minus whatever, Python is not going to give you an error. It's just going to give you an element of the array which you don't expect. That is a very interesting and subtle bug, so it's very important that you are aware of that. Okay, I already mentioned the shape attribute. So basically the shape of A is going to be the tuple 2, 3, 2 rows, 3 columns. And I can do that for vectors as well, for one-dimensional arrays. And as I already mentioned, you get a 1 tuple for that size. And of course, if I want the number of rows, easy, I can do shape 0. This is going to give me the number of rows. If I were to do 1, I get the number of columns. Okay? So no surprises there for Python users, of course. Okay, another thing which might be a little surprising, let's do a little experiment. Let me start just with an ordinary Python list. Okay, so I've got L, and I'm going to define a number of elements. Let's say range, I'm going to make life easy. No, I should not do that. Use list. Range, let's say 1 to 5, no, 1 to 10. Okay. And if you look at L, you'll see I get 9 elements. Nothing unexpected here. Okay. Now I'm going to define a second list, and I'm going to create that by slicing. So I'm going from my third element up to, I don't know, the sixth element, well, the fifth element essentially. Okay, so L1 contains elements 3 up to 6. All right. I don't think this is surprising to anyone who is familiar with Python. I'd hope. Okay, so no problem. If we do slicing, we get a copy. Easy. Do we get a copy? Let's check. If I change, for instance, the second element of L1, I change that to -1. Okay, L1 is changed, no surprise. L is, oh, okay, that should have been lowercase. I accidentally hit caps lock. So L is unchanged. And this likely doesn't come as a surprise. Okay, so of course we can do similar in MATLAB. I can have an array, let's call that V, and I'm just going to do the same thing, a range. And I'm happy with an integer array, I don't care in this particular case. So I just do a range 1, and I get really the same thing. And as you can see, V is this. Okay. Just as I can do slicing with Python lists, I can do slicing with arrays. So V1 is going to be V, and let's do the same thing. What was it? I went from index 2, I think, up to what? 2 up to 6. Okay, V1 is this array. So all the same thing. Now I'm going to modify V1 I'm also going to put the second element to -1. Okay, V1 has changed. Who cares? Let's have a look at V. And this is interesting because V changed. Oops. That might come as a big surprise. Okay, so in fact, when you slice an array in NumPy, you don't get a copy. You get a different view on the same array. And that's a little weird. It might be a little counterintuitive, but why would that be the case? Why is no copy made? Maybe there's a good reason for that. The answer is yes, there is a good reason for that. So the question is, of course, what good reason might there be not to copy, but rather to create a different view on the same array? The answer is again in memory bandwidth. So if I make a copy of some data structure, be it an array, be it anything else, I don't care, what I'm going to do is I'm going to transport that entire data structure, all of the numbers in an array, to the CPU, and then send them back again to a different location in memory. That's how things work. Can't help it. That's how CPUs operate. So basically, that means that if I have an array of 1 billion elements, and I slice 1 million elements out of that, so 1,000 of that data, if I were copying, I'd have to move those million elements to the CPU and then back into memory to a different memory location, and that would take quite some time. Now in NumPy we are concerned with performance, so we don't want wasting bandwidth. Okay, so the default is don't waste bandwidth, don't copy, create a view. If you want to copy, no problem. I can do V2, and that would be V1. I slice from, now I forgot again, 2, 6, and I create a copy. Okay, now this is V2. Yeah, I should have, sorry. I want to do this from V1. Okay, so now I've got my copy, and of course I've got -1 in the first position because obviously I'm making it, the V was changed. Okay, so let's again modify V2 now, and I'm going to modify that second argument, and I'm going to put it to 13. Okay, V2 of course is changed, but now V itself is unchanged. Okay, 13 here with -1 there, and of course it should again not come as a surprise because I've made a copy of my slice. And then, of course, I get it in a new memory location if I modify the element. That's the ordinary thing which you might expect. So in NumPy, copy is opt-in typically, and view is the default. And for performance reasons, that is a very reasonable choice. Of course, if you are not aware, and then you can introduce very interesting and subtle bugs in your code, which will not be that easy to find. So this is something that you really need to be aware of. Okay, I can do two-dimensional slicing as well. Let me create a somewhat larger array B. And again, I'm just going to use a range because again, I'm just going to fill it with integers. I don't care. So essentially, I'm going to do it this way. So I've got 24 elements, and I'm going to reshape it into let's say 4x6 matrix. Okay, as you can see, B has 4 rows and 6 columns. Okay, so I can take a slice out of B. For instance, I can take from the second row to the third row, so that would be 1, 3, and from the third column to the last column but one. Okay. And then you see I get 9, 10, and 15, 16. So indeed the second row, and this is non-inclusive. So basically I will not get the 11 and the 17 because it's non-inclusive. It's just the ordinary Python slicing. Okay. And of course, again, if I assign this to something, to C, for instance, and I would modify C. So, for instance, I set the first element to 2. Yeah, this I shouldn't do because then I have conversion. Let's say to minus 17. It's changed as well. Okay, that's something that you need to keep in mind. And of course, I can do slicing with strides and so on. It's just Python slicing, so everything you can do with Python lists, you can do with Python arrays. Just remember, list slicing copies, array slicing give you a view. And that is true in general. So quite a lot of NumPy functions will in fact return a view rather than a copy. And copy is opt-in. But it's not always the case. So it's always useful to check NumPy's documentation to see whether a function returns a copy or a view. If you make a mistake and you expect a copy, you will maybe introduce some very interesting bugs. If you make a mistake in the other direction, you think it's a view and in fact it's a copy, then you will have a performance issue. So it's important to check. Okay. Yes, one thing which is important also is strides. Let's have a look at B strides. That's also a property of matrix, well, of an array. And then you get the result 48, 8. Okay, what does this mean? So if you look at the numbers, you notice that 48 is in fact 6 times 8. And we have another 8 there. We also have 6 columns. So the first element of the tuple indicates the number of bytes which I'd have to move in the linear representation of my two-dimensional array in order to get to the next row. Okay, let's see. We know that by default we get something which is 8 bytes because this is an int64 array. Let's check. int64. So int64 is of course 8 bytes. So if I move 48 bytes 6 times 8 to the right, starting from, for instance, the first row, first column, okay, 1, 2, 3, 4, 5, 6. I end up first element, second row. Okay. So then, of course, it's pretty obvious what the second number means. 8 bytes. So that's how to get to the next column. And that's just a single step. So what does that tell me? It actually tells me something which is pretty important, and that is that arrays in NumPy, by default, are stored row-wise. So row major order. We have first the first row, then the second row, then the third row, and so on. Why do I mention this? Again, because there is an important difference with respect to MATLAB and with respect to R and to Fortran. Because in those languages, arrays are stored column-wise. So you first have the first column in memory, then the second column, then the third, etc., etc. So that means that data which is next to one another in memory, in NumPy lives on a row, in MATLAB and in R lives on a column. So that means if you're iterating over an array, a two-dimensional array in those languages, you would actually have the row number in the inner for loop, while in NumPy, in C, C++, and those languages, you have the column as the inner for loop. And that's important for performance. Why? Because actually, if you ask for a number in an array, you don't get a single one. You actually get 46 bytes, or in other words, you get 8 double precision floating point values or 8 in 64 values at one go. So if you use them in the next iteration, that's smart. If you don't use them in the next iteration, that's a bit less smart because you're suboptimally using your memory bandwidth. That's a precious commodity. Try to use it optimally. So important to know, row major in NumPy by default. You can choose. You can also have it in column major. That's also possible. That's just a specification which you can do. Let's see whether I can get that done. So because I don't do that often, so I might not get it right, but let's try. So we have D, and D is an NP array, and I want a two-dimensional thing, so let me do it this way. 3, 5. Should add square brackets here. Otherwise, that's not going to work. I have a list of lists, so let's say 7 and 9. Okay. So D is a 2x2 array. No, but that was not what I wanted. Sorry, I need an additional argument, and let's format. And let me put that to F. It doesn't want format. It's possible that this just does. Okay, now it did something. Okay, let's have a look at the strides now. And indeed, we have 8 and 16. So now the ordering is not row-wise, but column-wise. To go from one row to the next, I need only 8 bytes. To go to the next column, I need 16 bytes. So basically, if I show you D again, go from 3 to 7. Since now we have Fortran order, the F is for Fortran, this is column major. So basically these elements 3 and 7 are next to one another in memory. So I only need to move 8 bytes in order to get there. To go from 3 to 5, I need to move 1, 2 times 8 bytes, and then I'm there. Okay, so this is nice in NumPy. It's very easy to pick the order in which you want your data to be stored, but you have to be aware of that order. And probably, I've never tried this, so let's see. Is there an order? No, there is no order argument. Yeah, that is unfortunate. Somehow you should be able to get that value. Look up in the documentation how to do that. But remember, the default is row major, or in other words, C. If I change this to C, you will see that now the strides are reversed. Matrix looks the same, but you've got another ordering. Okay, let's switch back to the slides for a second. So I told you this, assigning to a specific element, blah, blah, blah. So there are no surprises here. So one of the things which you might notice, because it's kind of interesting, in fact, in order to use two-dimensional indexing or indexing of 2D arrays, you actually don't have to specify a tuple, and that's just a syntactic thing in Python. It is just automatic tuple packing and unpacking which is going on. And the most important thing, of course, I already mentioned a couple of times, is zero indexing. Okay, so the idea is to depend on the way we calculate? Yes, indeed. That is one thing which you can indeed do. Depending on how you access or plan to access your elements in the array, you can actually pick the ordering which is most suitable, indeed. So that is something which you can play with, which you can try and do. Sometimes, yeah, it doesn't really help because you need it sometimes in row order, sometimes in column nature. So yeah, then of course you're kind of lost, but yeah, that's the idea. You can do that if you want to. Or you can change your algorithm accordingly. Okay, so this is the array slicing. Ah yes, of course you can use the column to just get everything on a row or everything on a column. So if I specify a column 1, it means I want all the rows and I want the second column. Notice that there is no notion of row vector versus column vector. We only have one-dimensional vectors, one-dimensional arrays. What you do with them is up to you, but there is no notion of one or the row vector or column vector in a one-dimensional array. What you can do, though, is create a two-dimensional array with a single row or a single column. For instance, let's consider V again. Okay, so this is of course a one-dimensional array. If I want to make this quote-unquote a column vector, I can reshape it. Then it should have, I think it should have 10 rows. Well, 9 would be better, and one column. And now you see that indeed it looks like a column vector. So this is something you can do if you want to. By the way, I had to think here, what should I put? 9, yeah, the length of that thing and so on. You can actually do something nice with reshape. And that is having -1 for one of the dimensions. And -1 is going to be figured out from the actual shape of the object you're reshaping. So in this case, I want one column. Yeah, there's only one way to do that, and that is by having 9 rows. So this will do the exact same thing without me having to think, should I put 9? Has it 9 elements? Has it 10 elements? What does it have? I don't know. So basically, the -1 in reshaping is nice. To give you another example, I can also do np arrange. Let's say again 125 1, and I want to reshape that so that it has 6 columns. Okay, put -1 for the number of rows, and I want 6 columns, and the right thing happens. So using this -1 in reshaping is actually really convenient because you don't have to think, you don't have to make sure that you get the right thing. Okay, so this is slicing, nothing special there, subarrays, list slicing, etc. I already mentioned that. What you can also do is something pretty neat, and that is smart indexing. So I already have, well, I have an example here where I reshape something into a 3x3. Okay, and now I index conditionally. So rather than putting numbers here, I put a Boolean condition on the array. And this actually means I'm computing the modulo operation, so the remainder after division by 2. And if that's equal to 1, I'll actually change the array. So I'll only change the array for those elements that are odd, because those would have remainder 1 when I divide by 2. Okay, so that means that after executing this, I would get a 0 in the first row, first column, in the last column, first row, in the second column, second row, etc., etc. And that's indeed what I would get. So this is quite powerful. It allows you to very easily assign a value to certain array elements that have a certain condition valid for them. So what you should realize, of course, is under the hood, a 3 times 3 Boolean array is generated. So essentially, I can do that in 2 steps to show you. For instance, let me use B. It should still be around. Okay. So if I say, well, okay, B modulo 2 is equal to 1. Okay, as you can see, I get an array, same size as B, and of course, true and false values according to whether the number is odd or even. Okay, so if I assign that to something, let's assign that to E, drop to E. Okay, I can now do something like E is 101. Okay, if I can B, you see that every element where we had odd value is now replaced by 101. But the point which I want to make and why I do this assignment explicitly is that you should not be deceived. NumPy doesn't do anything intelligent here. It can't, because all of this is Python. So Python is first going to evaluate this expression. So it is going to create a large Boolean array, well, a potentially large Boolean array. If you use smart indexing with a 10,000 times 10,000 matrix, it means that under the hood, you will get another 10,000 times 10,000 matrix with Boolean values. That's going to eat up a whole lot of memory, and it's also not going to be the fastest thing you've ever done, because you need a lot of memory traffic. Okay, you can also use a function for that, which is npwhere, and that would actually replace all the elements of A that are larger than 0 by 1, and all the ones which are less than or equal to 0 by -1. So basically, in this particular case, it would just replace the zeros by -1 and everything else by 1, and you would end up with this matrix. But again, this is a Boolean matrix which is constructed. So just keep in mind that if you have large data, fancy indexing is fancy, but maybe not so very efficient. Okay, so we've been talking a lot about arrays. What can we do with arrays? Oh, we can do any scalar array operation. So I can add a number to an array, which means add that number to each element of the array. And I can do that with subtraction, with multiplication, with division, with floor division, and with the power operation. Okay, I can also add, subtract, multiply arrays element-wise, and then I just use the normal operators just as I would do on numbers. So this is of course different with respect to MATLAB. In MATLAB you would use the element-wise operators, which are dot plus, dot star, dot caret, etc., etc. So in Python it's automatically element-wise. So that means that we need something special for the matrix multiplication or the matrix vector multiplication. And this we can do either with function dot, or it can be done with the add operator, which is in fact a Python operator, which isn't used much. You can use it on NumPy arrays, hooray, hooray, and you can also use it on the array module elements which are in the standard library of Python. Okay, so that's your basic matrix arithmetic, nothing special. Of course, if you element-wise add two arrays, they should have the same shape. That's pretty obvious. If you have a matrix product, of course, they should have appropriate shapes. They should have the same number of, well, they should share, the first matrix should have the same number of columns, then the second one has number of rows. So the usual logic applies. Okay. One of the things which you should not do is use for loops to initialize or to apply a function to an array element to create a new array. So in this particular case, I have A, and A is empty. It's a 500 by 500 matrix. I really don't want to initialize it. Why would I do that? Because what I want to do is assign to each element of A the square root of the corresponding element of B. So why would I waste memory bandwidth by assigning something to A? So that's why I use np empty. And then B is initialized from a random distribution, same shape, no problem. And then of course I could do something like this: for I in range 500, for j in range 500, aij is equal to square root of bij. Okay, MATLAB people know this is a very bad idea, and indeed it also is a very bad idea in NumPy. What you should do is use the square root function in NumPy, and that is going to operate on all the elements of the array you give as argument. And it will produce a new array where each array element is the corresponding one in B, but with the function applied. The performance difference is quite large. So of course numbers will vary. If I do it now on my computer, I would get different numbers, but the ratio between those numbers of course remains the same, and it's a factor of 21. So this is quite important. Always use NumPy functions on arrays if you can. All right, so of course we have lots of other functions, all the trigonometric functions, hypertrigonometric functions, exponential function. We also have things like trace, transpose, and so on and so on. Okay. A little bit of linear algebra. As I already mentioned, there is just a little bit of linear algebra because there is another package which has a lot more linear algebra, but there is some in NumPy. For instance, the matrix power operation. We use the sub-module linalg and then the matrix power operation. So remember, the star-star operator, which is the power operator in Python, is going to be element-wise. So let me perhaps illustrate that. Let me create a square matrix. If I want to do a power operation, I need a square matrix. So let's say F is, I don't know, the array, let's take one by hand, -1.3, 5.3, 7.1, and -1.5. Okay, so this is a square matrix, no problem. If I do this to the power 3, that's what I get. Okay, that may or may not be what I want, but what is happening is that I get the third power of each element here. That is not power operation on matrices. If that's what I want, I can do linalg matrix power, and then we get F at 3, and then we get something quite different. So this is just multiplying F by itself and by itself. So we should get the same thing if I do F multiplied 3 times itself. And indeed, we get the same result. Okay, so this is matrix power. The other thing is element-wise matrix power. Okay, so we have the inverse, we have the determinant, etc., etc., all the usual suspects which you have in general, and even eigenvalues and eigenvectors. So I didn't mention eigenvectors, but I think you can also compute them. Let's see. And let's see what eigenbills we can do. Yeah, we can have, yeah, okay. So there's nothing specific. Let's see what happens now. I don't know. I've never tried this. So let's see. Okay. Then you get two things. The first thing is an array with the eigenvalues, and the second thing is a 2D array with the eigenvectors. So yeah, but there is a special function for the eigenvalues, apparently not for the eigenvectors. Okay, makes sense because typically you want either both eigenvalues or eigenvectors, or just the eigenvalues, and you're not interested in the eigenvectors. The case where you just want the eigenvectors, I don't really know why you would want that. Anyway, references versus copy, we talked about that at length. I showed you, so that's important. Okay. Let's have a little look at I/O, because there are some performance traps there. So I'm going to read a text file that contains 1 billion double precision floating point values, but in textual representation. So there are quite a number of functions in NumPy to read arrays from text files, and one of them is from text. So if you do that, you see that it takes quite a long time. Actually, it takes almost an hour. And very interesting, it also uses 44 gigabytes of RAM. Why on earth would it need 44 gigabytes of RAM? Because storing 10 to the 9th 8-byte values, that should take 8 gigabytes of RAM, not 44. So what the heck is going on here? Okay, but there is a different function, and that's from file. And if you specify a separator, that allows you to read the text file. And as you can see, it's much faster. So it takes only 4.6 minutes rather than an hour. So that's already good. And it only uses 8 gigabytes of RAM, which is actually just what I expect it to be. I mean, that's what I would want to have. Okay, so that's a factor of 12. That's quite a lot. So there are many functions in NumPy that do sometimes the same thing, but there are some things that you should be aware of. And for instance, this from text function is really, really crappy. So it's probably still there because of backward compatibility, but the person who wrote it, well, should be shot. What is going on? If you look at the source code, which at some point I did, then you see that in fact what it is doing, it is reading that text file and it's creating a list of lists. And then it's going to convert that list of lists into an array. And that, of course, takes a lot of time on the one hand and takes a lot of memory on the other hand. So yeah, that's not the best implementation I've ever seen. However, if you're dealing with large data, you might actually want not to store it in textual format, but rather in binary format. So if I have a binary file with those same billion numbers, but now in binary format, I can actually read it in 8 seconds rather than 4.6 minutes. And that's a factor of 35. So you might want to consider for intensive I/O, binary I/O rather than text I/O. And of course, dealing with binary files is annoying, but that's why we have, for instance, HDF5 or NetCDF to make life a lot easier. And that's something which we will also cover later on in this training. Okay, so don't use this. There is NP matrix, and it behaves a little bit like MATLAB. You recognize this is a row, and as a second row, you have the semicolon thing. It's represented as a string, and it might seem a good idea. It also overloads the star and the power operations so that they actually do matrix multiplication and matrix exponentiation. Don't use them. It's not a good idea because it's going to be confusing. You will mix them up with NumPy arrays and it's going to be a mess. So I'm mentioning them because you might like them if you come from MATLAB. Don't yield to the temptation. Just use NumPy arrays as it was intended. Okay. So basically for the MATLAB people or the people who think, well, okay, maybe NumPy is not such a good idea, MATLAB is better. This is a very reasonable article that compares MATLAB to NumPy. And personally, I'm not a big fan of MATLAB, to be honest. So I asked one of my colleagues, who actually is a MATLAB fan, to read the article and give his opinion. And he thought it was a very balanced article, which really weighed the pro and cons of MATLAB versus NumPy quite objectively. So I would recommend this article if you're still in doubt whether to use MATLAB or NumPy. And of course, both are very nice. I mean, as such, there's nothing wrong with MATLAB. It's used quite a lot in industry, so it's quite useful to know. I'm not a big fan for a number of technical reasons, but that's not to say that it's a bad thing. Okay, this seems like a good point for a break. And after the break, we'll discuss some SciPy libraries, well, modules in SciPy, which can be useful for scientific computing. Okay, if there are any questions during the break, just type them in. We'll have a break till, let's see what the time is now. The time is 43. Okay, let's make that till 55. That gives you 12 minutes to grab some coffee and so on. That should be enough time, I think. So 10:50, we'll resume. No, I had said 55, I think. Yes? Yeah, 55. 12 minutes. Okay. Again, if there are any questions, feel free to type them in the chat. I'll have a look at them while I fetch coffee and new tea and so on. Okay. Okay, let's continue. The first thing I'm going to do, before I forget, is to make sure that I've got your names for your certificates. All right, I need to save that. Let's say 3:14. Oh, it's Pi Day. Oh, I hadn't realized. Okay. Should have thought of it, then could have given a Pi Day example, but no, I don't have anything handy, so let's not go there. Okay, let me share my screen again, and then we can continue. That will be here, and okay, and there we go. And here's the screen. All right, so let's talk a little bit about SciPy. So NumPy is basically your basic building blocks. It gives you mostly data structures and elementary algorithms on arrays. But of course, there's much more to scientific computing than just arrays and matrices and vectors. And that's where SciPy comes in. So SciPy is built on top of NumPy, which is of course a nice thing because it means that it uses data structures which are pretty performant. And so let's talk a little bit about SciPy. Of course, SciPy is really, really a huge library. So for instance, it has linear algebra, not only for dense matrices like NumPy has to some extent, but also for sparse matrices. And that's of course already an interesting thing because in many domains you need to work with sparse matrices because they are too large to store in a dense format. Also, for instance, solving sets of ordinary differential equations. There's quite a lot of software for that, and I'll show you an example later on. Numerical integration, optimization, interpolation, etc., etc. All that kind of things can be done with SciPy. There's also a whole library of mathematical and physical constants, which is easy because then you don't have to define them yourself. You don't have to define them by hand. And of course, many special mathematical functions, Bessel functions, other special polynomials, and so on, are all available. So that's quite easy. Importing SciPy is usually done, import SciPy SSP, as usual, and sometimes you have to import subpackages explicitly in order to get them to work. So for instance, we can do some linear algebra. So in this case, matrix decompositions, and one of them is singular value decomposition. And those of you who are familiar with MATLAB will recognize this because we can just do SVD and we get the U, the S, and the V matrix, so the decomposition of that array. And then S are the singular values, and U and V are vectors that allow you to, that form decomposition. So there's some more NumPy here. I can create a diagonal array, diagonal matrix out of a vector by just using the npdiag function. You have something very similar in MATLAB, by the way. And of course, the MATLAB people will have already noticed that many things, many names in NumPy and SciPy have actually counterparts in MATLAB, and that's of course because the developers of NumPy and SciPy have taken quite some inspiration from MATLAB. Okay, and then we can reconstruct our original matrix by multiplying U, S, and V, and then As you can see, we get very small differences up to let's say 1 to the power minus 15, and that is indeed 15 digits of precision, which is really expected for a double precision number. Okay, so basically such operations should be very fast if and only if NumPy and SciPy have been properly installed. So basically, if under the hood they use proper BLAS and LAPACK implementations. How can you tell? Well, if you're using a Conda environment, typically you're good. And we can have a look at this. If I can find my terminal, which is here. So what I can show you is Mamba list. So basically the list of packages which is in the package which is currently loaded. And one of the things you notice there, if I go through it, is MKL. So basically what you get typically when you install a Conda environment is under the hood a runtime library for the mathematical kernel library, which is developed by Intel and which contains an optimized version of the BLAS and also an optimized version of LAPACK. And as you can see, there's also MKL stuff for doing a fast Fourier transform and also for generating sequences of random numbers. And this you typically get automatically when you have a NumPy library. If not, if you're not using Conda or whatever, always check. The easiest way to check, for instance, on HPC infrastructure is to see what other modules are loaded. And if you see something like either OpenBLAS or MKL, normally you should be good. What you never ever should use is the netlib implementation of BLAS, because that's a reference implementation. It's quite important. That is used as a gold standard for correctness, but it is really, really slow. So if you see netlib somewhere in your list of packages, then you might get suspicious and you might want to check your installation, because you would be running with very suboptimal speed. Okay. So basically, there are other decompositions. Of course, you've got QR decomposition, many others, etc., etc. So that's your linear algebra in part. Another example is linear regression. So we have our data file. It contains an X and Y column. And I also use this example in order to show you something which is cute. I'm going to read my file using gen from text. Of course, gen from text expected values in a row to be separated by spaces. So I have to specify the delimiter, and the delimiter in this case is a comma. So it's an optional argument if you don't specify it in space, but you can specify something different. And I'm also specifying the d-type, so I want my values to be floating point numbers. And note, there's also an optional names attribute which is true, and that means that the column names will be taken into account. And it's kind of nice because it means that I can address a a column of my data as if data were a dictionary. I can just say, okay, I want the X column of data. And that's something which is kind of cute, that you can actually just access your data that way. And to do linear regression, okay, that's in the stats subpackage of SciPy. And it's just a linRegress function. You specify X coordinates, Y coordinates, and you get the slope, the intercept, R, and some other error measures back. So that's very easy to do. Optimization, so finding the minimum of a function. Maybe let me show you that in a different way. Let me open up a notebook, which is kind of cute and which also illustrates how to solve differential equations, which is kind of nice as well. So let me take this example here, Canon.py. it shows quite a number of things. So as you can see from the requirements, I'm going to do my plotting with Bokeh, not with Matplotlib as I usually do, but with Bokeh, which is a nice library, and I'll show you why I do that when we go to the notebook. As you can see, I'm going to use NumPy, I'm going to use SciPy, I'm going to use integrate. That's for solving sets of differential equations, ordinary differential equations, and I'm also going to use optimize. And note, I'm also going to use SymPy. So SymPy is cute. That allows you to do symbolic computations in NumPy. So what am I going to do? I'm actually going to solve differential equations, the differential equations which describe the trajectory of a projectile that is fired by a cannon. And of course, if you don't have any drag, then that differential equation is fairly straightforward, second order differential equation, and the only force which acts on the thing is the gravitational force. That's it. So that's very easy. So we define the constant g, which is the gravitational acceleration, 9.81 meters per second square. Okay, so how do I solve this? I can't directly, in the sense that there are no packages that numerically solve higher order differential equations. But of course, I can easily turn this second order differential equations into two first order differential equations by just introducing a vector v, which is the velocity, and then I get dr dt is v, and dv dt is minus g ey. Okay, so how do I encode my equations? Very simple. I just have to look at the right-hand side of the equations. So I have to write a function which takes the time as a first argument, which takes the function values I'm getting as the second argument, and which takes any number of parameters, in this case just g. Okay, I'm unpacking y, because y is actually an array, and I'm using tuple unpacking here in order to get x, y, which is the x coordinate and the y coordinate of my system, the velocity in the x direction and the velocity in the y direction. Then, of course, I can compute the velocity itself, which is the square root of the x component squared plus the y component squared. Okay, and my equations, so basically dx dt is going to be v of x. dy dt is going to be v of y. Dvx dt is going to be 0 because there is no force acting in the x direction, and dvy dt is going to be minus g because that's the gravitational force which acts in the opposite direction. Okay. What I also need to do or can do is specify the Jacobian, so the cross derivatives for this particular equations. And these are the cross derivatives. Apologies. The cross derivatives of the right-hand sides again. And so basically, nothing much fancy happens here. So in this case, it's very easy to compute the Jacobian. The only non-zero terms are the ones for the first two equations, because of course that is 1 and 0 in these positions. All the rest is 0 because there is no x, no x, y, and vy in the first equation. There is no x, y, and vx in the second equation. There is nothing in the third equation and nothing in the fourth equation. So basically we get a number of rows which are 0. Which are all 0. Okay, so as you can see, all of this, both the right-hand side function and the Jacobian function, return NumPy arrays, a one-dimensional array for right-hand side, a two-dimensional array for the Jacobian. and they take the same arguments. This is just for symmetry because, of course, I'm not really using G in the computation for the Jacobian, but it's just for symmetry. Okay, so preparation done. Now I can create a function that computes the initial values. So basically the exit velocity of my cannon, of my projectile rather, in my cannon is 700 meters per second. So that's V0. And then of course I can compute the initial position, that's 0 for X and Y. I just take the origin at the location of the cannon and the initial velocities, which are just the cosine of the angle which I aim the cannon by. And so basically I first do a computation in the sense that I go from degrees to radians, and then I use the cosine and the sine for the initial velocity. Nothing special, nothing interesting. So the first thing I do is I create my initial values, no problem. And then things get more interesting. In the integrate module, I have the ODE function. And what I need to specify for ODE is the right-hand side function and the Jacobian function. And then I set properties. So I set the integrator, and that is essentially the method I'm going to use to integrate my my system of equations. And in this case, this is something, a slight variant on a Runge-Kutta full 5 method. So we have quite a number of integration methods. Check the documentation to see what is available and pick the one which is suitable for the system of differential equations you're solving. We also set the initial values. So both for all the functions which we're trying to compute, so x, y, vx, and vy, and also the initial time, which is 0. So that's the second argument in initial value. So the first argument is in fact an array of values or a list of values. Then we set the parameters for the right-hand side function, that's just g, and also for the Jacobian, which is also g. So this sets up my system of differential equations, my solver. I specify a delta t, which in this case is 5/100ths of a second. And I also set up an array, well, a list of values essentially for all my values so that I can plot them easily later. Okay, so while this is successful and y minus 1, that is essentially my last value, when that's larger than or equal to 0, so if the altitude of my projectile is positive, in other words, if it hasn't hit the ground yet, I'm going to continue. And in each iteration, I do an integrate step for cis t to cis t plus delta t. And in cis t, I've got t, which is the current time, and y, which is the computed new values. So y0 is, of course, the x-coordinate, y1 is the y-coordinate, etc., etc. Okay, and then I can make a plot of that, and that's very unfortunate because I will have to evaluate the whole lot. Can we use Euler method? If you're suicidal, yes. So basically, indeed, if the problem with Euler, of course, is that you very soon have troubles with convergence. And for instance, even for this very simple system, you will not have convergence, and you will, in fact, if you plot the energy, you would note that the energy is in fact increasing. So the Euler method, even for this very simple system, is not going to converge. So I'm really not a fan of Euler method. You really have to be sure that it converges in the domain you're considering. Okay, I'm going to quickly evaluate this anyway. First, that's the drawback of Bokeh. it doesn't retain its output. That's a little inconvenient in notebooks. Okay, let's stop this. And as you can see, I get the trajectory of my projectile. Okay, so one of the things why I like Bokeh is basically that you automatically get these tools here. And so basically I can zoom in, for instance, by mouse. So now if I use the zoom button, I can zoom into my plot. I can also pan. So basically I can, okay, if I click it, I can actually pan my function. And now I can both zoom and pan because both are active. So basically I can just zoom into the top of my parabola, etc., etc. So that's kind of cool with Bokeh, and I can just click reset and I get my original back again. So that's a nice thing about Bokeh, so that's why in this particular case I used it. Okay, so of course the range is a function of the firing angle, and the range would of course be simply computed by, again, integrating, but just retaining the last point before you hit the ground. That would give you the x at that point, and that's what you're interested in. So we could do that. This is a function which does this. Okay, I can evaluate it. And then I can do that for many values of the angle, in this case for 50 values. So I'm going to check what happens, what's the range with an angle of 10? What's the range with an angle of, I don't know, 10 something? And the last value would be the range when I have an angle of 80 degrees. Okay, so this can be computed. I'm not going to do that because this takes a while. No, this should not take a while. This should be pretty fast, actually. Compute range. No, yeah, because I have to, no, this will take a long time, because I would have to compute 50 times. I'd have to solve the set of differential equations, and that's going to take quite a long time. So I'm not going to do it for 50. I'll just do it for 10. That will still take a while, but might still be more or less feasible. It should be something like, I don't know, probably 20 seconds or something like that. Meanwhile, while we wait, I'm going to continue. And this, in this case, I want the maximal range. Okay, it's already done. So let's show the plot. And as you can see, it's likely, we can't see it here, that the maximum is actually going to be around 45 degrees, which is not really a surprise, I would say, for a projectile without drag and without any interesting stuff. Okay, so if we want the maximal range, what we should do, of course, is optimize the range function. Now, the optimization function is in fact optimizing for a minimum. So I need a small helper function which just computes the range and returns the negative. We also do this with a lambda function. Would be more elegant, but whatever. So I can use the optimize scalar function in the optimize package. So I specify the function which I want to optimize, and then I specify a bracket. In this case, I use a bracket between 10 and 80 degrees. And I can pick the method. So in this case, I want to use a golden ratio method. Okay, so if I do that, and I'm really not going to do this because it takes quite a while, you see that the maximum range is going to be minus 49,000 something. The minus sign is of course because I have to minimize. So of course the range itself is going to be 49, well, almost 50 kilometers. Okay. And the angle, which is optimal, is 44.975 degrees. So given the precision by which I'm doing this, yeah, it's 45 degrees. But yeah, the precision is somewhat limited here because this really takes a while, because essentially I need to solve a set of differential equations for each point that this minimization method is going to try, and it's going to try quite a number of values. So that's why this would take a while. And as you can see, the number of function evaluations is in fact 44. So in order to reach this level of precision, I already have to run my function, so solve a set of differential equations 44 times, each time with different initial conditions. Is it better to use solve IVP instead of integrate in general? Well, I don't know. I really can't answer your question, to be honest, because I would have to check what solve IVP does. I don't know. I'd have to verify what it does. I don't know. Can't answer. Okay, let's make things a little more interesting by introducing drag. So essentially, this is our equation. So we have a term which depends on the velocity. So this is basically friction, air friction. And we also have a factor which depends on the altitude. And that, of course, is going to take the influence of the air density into account. And this is exponential, negative exponential. So that is taken into account here. There are some realistic values here, blah, blah, blah. So again, I have my right-hand side of my equation. Now, of course, it's going to be more interesting because we actually have components for the differential equation of Vx and Vy. Of course, differential equations for x and y don't change, but those for Vx and Vy do change. And now, of course, we also have one in the Vx direction. And in fact, there is a problem here, because this should be absolute value. But okay, because Vy can be negative, and then that would be interesting. We would get positive friction, which is kind of physically not really a good idea. So I should add an absolute value here. Let me do that. Vx it doesn't matter because that remains positive anyway, but for Vy it will change sign and then we get weird things. Okay, so now the Jacobian, I'd have to compute the derivatives of these equations with respect to x, that's easy, y, that's sort of easy, Vx and Vy, and that's going to be messy. So of course I could do that, I could take pen and paper and do that. I could also just use SymPy to do a symbolic computation. So the first thing I do is I create a number of symbols. And I do that using the SymPy symbols function. That takes a string, and that string is delimited by spaces. Each character sequence here denotes the name of a variable. So I have variable b2m, I have a variable v, y, yd, vx, vy. Okay, so now I've got a lot of symbols, and I can get a symbolic expression for v, because that's just the x component of the velocity squared plus the y component of the velocity squared, and the square root out of that. Okay. Then I can create a symbolic expression for the right-hand side of the differential equation for Vx, and that's just minus bm times v times the exponent of minus y divided by yd times Vx. Okay. Then we have, I can differentiate the right-hand side with respect to y, and that gives me this expression. I can do the same thing for Vx, etc. So basically that allows me to easily compute my Jacobian. And then I can define it using the expressions which were computed. Okay, so if I define my constants, I can... Yes. So the notebook is in the GitHub repository. It's actually at the top level. Let me try and find my repository. It's actually in the source code directory. And it's here. This is the one. So basically, here I do the same thing. So I just integrate, same solver and so on. So nothing special is going to happen here. I have the same delta t, I compute and I plot. As you can see, I get a trajectory, which is no longer a parabola. And that, of course, is what you would expect, because basically due to drag, we have less and less energy. And basically at the end of the day, we will have a much shorter range and also an asymmetric range. Okay, so we can compute the total energy, which is the sum of the kinetic energy and the potential energy. Since I frankly don't really know the mass of such a projectile, I just compute E divided by M. Okay, so that's this function, and of course I have my x, y, v, x, etc., etc. So I can simply compute this, and then that's what we get. And this is slightly annoying, because in fact we have an energy which suddenly increases. So basically the differential equation solver is not really entirely stable. So that is a bit of an issue. The energy should decrease monotonically. It's not, it's going up here. So basically that means that the solution is not entirely stable. So Euler would do pretty badly. This one is also not doing entirely right. So yeah, I'd have to check which method to use in order to really get a stable orbit, stable solution. Okay, so if you can't take the Jacobian, there are also methods that have the Jacobian as optional, and I think even by default you can do that. Let's have a look at the documentation. So that would be SciPy integrate and ODE. And then we have our documentation. And let's see what we need to specify and what we can specify. So the Jacobian is optional, so we don't need to specify it. But of course, it would speed up computations in the sense that certain stepper methods, in fact, require it, because they need to be able to compute the Jacobian in order to compute the next, well, to compute the size of the steps and so on. So depending on which integration method you're actually going to use, you might actually want to specify it, because otherwise it has to be approximated numerically, and that would take much more time. So that's why typically you would like to do that. Okay, so we could do the same thing with maximal range. Not going to do it because, again, it would take quite a while, but now we would have a range of 26 something kilometers. Okay, so in summary, I showed you a little bit how to use the ODE function, the integrate module of SciPy. I also showed you how to use the minimum scalar function, which basically minimizes a function in a given interval. And I also showed you a little bit about using SymPy in order to do symbolic computations in Python. Okay. let's return to the slides for a second. So basically, this is same thing, but actually with a different function. So here I'm using fmin cg. That would also do a minimization of a function, but it's not bracketed, but rather we specify an initial value. And then you have different methods. For instance, this is conjugate gradient, as I mentioned, but you also have Powell's method, BFGS, Newton conjugate gradient, and so on. So that would have been an alternative to the one I used to compute the maximal range of my cannon. Okay, so basically same story, but this is for an harmonic oscillator. And again, computation of etc. etc. Okay, so there are some other notebooks which you might want to have a look at. Let's have a look what we have. There should be one here. Dynamic systems. I think this is the one about. No, this is string alignment with dynamic programming. No, that's something entirely different. And let's discard this. That's dynamic programming. Yeah, of course. Okay, so I should have one about the harmonic oscillator somewhere, but I don't seem to see that. Maybe there is no. Yeah, there will probably not be a notebook about that. Yeah, pendulum. So there is a script which does that, which solves these equations. Okay, so basically more of the same thing. Let's talk a little bit about signal processing. So this is actually, in a way, a nice story, and that's why I want to briefly talk about it. So at some point, I was discussing with biologists, and they wanted to do something. They wanted to count nightingales. Now, nightingales are active at night, which is kind of inconvenient if you want to count them in a certain region. So they thought, well, okay, can we put microphones in that area, make recordings, and then try and count individual nightingales based on their sound? Okay. So of course, in Belgium, you have a lot of noise due to roads, etc., etc. So the first step in this whole thing was, in fact, noise cancellation, getting rid of the noise in these recordings. And for this, of course, you need to do some signal processing. And okay, back in the very old days, so in the middle of the 80s, I did have a course on signal processing, but since then, I frankly did not ever do anything with it because I was in the field of physics where signal processing was not really a thing. Okay, but yeah, I knew there was something like high pass filters, low pass filters, stuff like that, and yeah, so it seemed like an interesting challenge to see how far I could get with these particular signal processing tasks. So the first thing to do, of course, is to read your data. And one of the nice things in SciPy is that it also has an I/O module, which contains many functions in order to deal with different file formats, to read them, to write them, etc., etc. And of course, for sound files, you might want to use a WAV format. Okay, so I want to use the WAV file module and use the read method in order to read my data. So I specify a file name and I get the sample rate and the signal out. The signal is going to be an integer array. The sample rate is just going to be a number, floating point number. Okay, so of course, the first thing I want to do is to have some idea about the frequencies which are present in my signal. And of course, the way to do that is to compute a power spectrum, so a fast Fourier transform of the input. And that is quite straightforward. We just check how long our signal is, how many sample points we have, and we generate an array of frequencies, which is just essentially the sample rate times numbers divided by n, so between 0 and 1. Okay, and then we can use the fast Fourier transform, which is in SciPy, and that's just FFT, and we divide the whole lot by n in order to get the power spectrum. Okay, so if we do that, this is what we get. So this is the original signal. This is just the amplitude versus time. And you see, actually, it's a uint. Well, you can't see it, but yeah, let's say it's a uint integer, so unsigned. Okay, so this is our signal, and actually, we can try whether you can hear it. Maybe not. Oh, damn. Okay. So there is quite some noise, which you may or may not have been able to hear, but rest assured it's there. So basically, if you look at the power spectrum, then you see that we have a lot of activity going on around 3000 Hertz. There is also a little bit around 4000, a bit above 5000, and there is some stuff here around, I don't know, 100, 200 Hertz. And this is our noise. This we should get rid of, because that's what the signal is noise. So we need to get rid of that. Okay, so what we need is a high-pass filter, which allows the high frequencies to go through, which will dampen the low frequencies. That's basically the idea. Okay, so SciPy has a signal module which contains filters and so on. So what I want is an IIR filter, and I need to specify the order of the polynomials I'm going to use to create my filter, because it's a sum of polynomials, and I want to go to 17th order. Okay, I also have to specify a cutoff frequency, and that is in fact a Nyquist frequency, which has to do with the sample rate. That's easy to compute. Then I need to specify that I want minimal attenuation. So basically, I want to make sure that my signal is well, that the volume of my signal is decreased the least possible. The filter type is a high-pass filter, and I don't want any analog filtering. And the type of polynomials I want to use are Chebyshev polynomials. So that has to do with the 17 here. Okay, so basically I specify all these parameters. I fiddle a little bit with them in order to get things reasonable. By the way, people who really know something about signal processing tell me that 17 is really over the top, and that you can do with much lower degree than 17. Anyway, now I can apply my filter, and basically the first thing I need to do is to compute the base amplitude of my signal, because my signal in fact is uint 8, and I have to make sure that after doing the filter I have to add the base again, because that it will be based on 0, and I don't want it to be based on 0, because then you don't hear anything. Okay, so the filtered signal is just using that IIR filter, and basically it's a filter which goes back and forth essentially, and then based on the filtered signal, if I add the base to it again, then I actually get my wave signal. So pretty straightforward. I can write a new WAV file, again using the WAV file module in SciPy IO, but this time the write method. I have to specify my signal, of course, and the sample rate, and I give the file name. Okay, so not very spectacular, but why am I telling you this? Again, I didn't remember much from my course on signal processing 30 years later. So basically, question is, how long did this take me? Well, it took me like in total 1.5 hours, but that also included getting familiar again with the theory, because I had to look up what a Nyquist frequency was. I had to look up what an IIR filter was. I had to look up why it's a two-step process, etc., etc. And at that point, which is now like 8 years ago, I really understood it, and I really knew what the Chebyshev polynomials look like, and so on. So the whole thing was actually solved and understood in opposite order in less than 1.5 hours. And that's actually one of the nice things about these Python libraries. They allow you to do fairly sophisticated stuff in a very short time. And that's actually the power, because if I would have to do this in a language like C++, where I didn't have the ready-made signal processing stuff available, this would have taken me quite a lot of time. Now, just 1.5 hours, including reading up on Wikipedia about filters and about Nyquist frequency and whatnot. So that's actually a very nice thing. I can also now let you hear the end result. No, doesn't want to. Okay, don't know whether you can hear the difference, but there is hardly any noise left. And basically you see this because this peak, which was here around 100, 200 Hertz, is indeed has indeed vanished. And also you notice, because here this the signal between two chirps is much smoother than it used to be. Okay, so that's kind of cool. There is a lot more in NumPy. There's also stuff to do quadrature methods, so numerical integration, other things, interpolation, and so on. I've mentioned them. I may have some examples. I don't quite recall whether I have examples in the repository, but typically the documentation of SciPy is quite okay. And of course, as usual, you need to know your numerical methods. If you don't know, then you will have some trouble, because garbage in is garbage out. So trying to do something with the wrong method is going to give you bad results, as I illustrated with the energy function thing, which, yeah, the integration method doesn't really converge. So yeah, that's something to keep in mind. You need to know your numerical methods. If you don't, well. Okay. So one of the things we can talk about, let me look at the time, is briefly about Matplotlib. You're probably more or less familiar with that. So Matplotlib is a little bit plays the role of NumPy, but then in the plotting world. So many packages have been built on top of NumPy, and many plotting libraries have been built on top of Matplotlib. So Matplotlib is pretty low level, but it's nice if you want to do simple plotting, and if you want to do quite sophisticated things where you need a lot of control over your plot, then Matplotlib is really your friend. So basically, you can do all kinds of plots: scatterplot, line plots, bar plots, histograms, heat maps, even 3D surface plots if you really want to. So all kinds of things are possible using Matplotlib. One of the things which is nice is that you can actually have LaTeX formatted labels and annotations. So that's kind of cool. Okay, you can plot to screen, you can plot to many file formats, depending on what you've installed in your operating system. You need libraries, but if you have them, you can. And of course, with Conda, that's a lot easier nowadays. And you can also use them, of course, in Jupyter Notebooks. So basically, again, Matplotlib has quite a lot of features, and yeah, I can't discuss them all. I'll quickly show you some things. Let me just use the slides. So basically, I create some data using, of course, NumPy. So nothing special here. And I can now create a plot, plt plot x and y, and I can show the plot. In a notebook, I don't have to do that. In a notebook, this would be something along the lines of import plot SPLT. Okay, and then I can use magic matplotlib inline, and that means that when I do a plot, it will immediately be shown in my notebook. For instance, x is np in space between 0 and 1, and I want 101 points. Okay, and y is going to be np square root of x. Okay, now I can do plt plot y, and I immediately get my plot in my notebook. So in notebooks, it's really convenient and easy. Okay, if you're in a script, you can actually show the plot, then a window will pop up if you have sufficient libraries installed, and you will see the plot live. And this is what you would get for this particular data set. As you can see, it's actually the solution of a harmonic oscillator with damping. So the amplitude, which is on the y-axis, decreases as a function of time. Okay, and if you want to save it to something, for instance, PDF or PNG or JPEG, if you have the right libraries, SafeFig will have a look at the extension of your file name and do the correct conversion. Okay, so you can, of course, specify axis labels. And the nice thing is, as I mentioned, you can use LaTeX. So given that this is between $signs, I want mathematical notation. So t is a mathematical variable. It will be printed in italics. I can also use Greek characters. \theta means I want a theta symbol. I can fiddle with the font size that I want. So I can also do annotations. So this is a somewhat more involved LaTeX expression. And I can put that at certain coordinates in my plot. And these coordinates are just the coordinates of the axis. So that's a little bit different with respect to some other plotting packages, which I know. So they typically have a different coordinate set for stuff that you add to your canvas and the axis which you have on your canvas. So not so for Matplotlib. It's one and the same set of coordinates, which personally I like. Okay, so you would get something like this. Indeed, italics t on the x-axis, theta t on the y-axis, and this formula. Frankly, I don't consider it well rendered. If you compare that to actual output of LaTeX, you would notice quite a number of differences, and this looks somewhat ugly. Theta is too large with respect to etc. etc. So yeah, it's somewhat ugly. Okay, notice that I'm using raw strings here for my LaTeX, because basically LaTeX has a lot of backslashes, and hence it's convenient to use raw strings, because then I don't have, then backslashes are not treated specially. They just mean what they are, a backslash, that's it. So for having LaTeX strings in Python, or having regular expressions in Python, these raw strings are really quite useful. Okay, so basically to construct a plot, you can gradually do that. So for instance, I could now say, well, okay, I want to add an X label, so the X label, and I want that to be X. Well, very and as you can see, I've got my X label, and then I can add a Y label, I can add annotation, whatever. So that's typically what you do. You gradually construct, enrich your plot in order to get what you want. You can have multiple functions in one line plot, for instance. So I create some more Y data, and I can add those to my plot, just again with PLT plot and the data and some parameters. So the column here means I want a dotted line. The alpha value means I want it a little bit transparent. So 1 is completely opaque, 0 is completely transparent. So I want to make that line a little bit softer. I want it in red, and I also want it not to be as wide as normal. So the line width normally is 1. I set that to 0.9. Okay, and then I get something like this. Why am I playing with the line width and with the alpha value? Basically, if I don't, this will be very distracting. And the only message I want to give here is that the envelope of this particular curve is an exponential. So that these lines just need to guide the eye. They shouldn't really catch too much attention. Okay, so that's basically the line type. And you can also specify color and so on. So basically this would be, with more points, this would be the plot, and it looks quite nice. Okay, except for this differential equation, which I think is pretty crappy, but apart from that, it looks rather acceptable. You can also do histograms. So I'm going to read data from a file, and in this case I'm using yet another NumPy function, load text. Okay. And I have specified number of bins. And then I'm going to plot a histogram. So that's the hist function rather than the plot function. Specify the values, the number of bins. I want it normalized. I want the color to be red. And again, an alpha value which is less than 1. And I want X and Y labels. Okay, this is what I get. If I don't have this alpha value set to 0.6, this will be an entirely red blob, which is really not nice. You don't see the boundaries between the different bars here in my histogram, so it would really look ugly. So the alpha thing is basically cosmetics. It formats my plots in such a way that it conveys information more easily. That's the whole thing. And then, of course, I can combine that with a line plot on my histogram. So here I'm using SciPy again. I'm using the statistics package. And for the gamma distribution, I use the probability density function with some parameters for the gamma distribution. I specify the scale, and I specify this parameter here, which I've got what the name is, and then I just plot it. And as you can see, I get the black line here. And in this case, I have a broader line because I really want to emphasize this theoretical distribution and compare it to the sample distribution, which is the red histogram. Okay, so very easy. To get this plot, you need quite a lot of packages. You need SciPy stats for the probability density function, NumPy, etc., etc., etc. Why do they often add access first before the data? Okay, so this is not the way I typically do that. So let me see whether I have a good example. I typically don't do it this way, but what I do is question is, where do I have an example? Probably here, somewhere in Matplotlib. Let's see. Okay, I really don't remember what this notebook is, so let's have a look. Okay. What am I doing here? This is some data analysis. Yes, this is actually a good example. So the way I typically do that is I create subplots And then I get a figure and axis, and I work on the axis. So let me perhaps evaluate this thing. I hope it can still be evaluated. Normally, yes, but who knows? Okay. Yeah, well, that's some deprecation thing which I would have to check. This is really an old notebook. I completely forgot that it existed in the first place. So basically, I have quite some data here, and essentially, I have several axes. So, for instance, here I have an x-axis. I have two x-axes, and I also have two y-axes. As you can see, the left y-axis is different from the right y-axis. So on the left axis, you see the performance metric of supercomputers, and on the right axis, you actually see the rank of those supercomputers in the top 500 of supercomputers. So this is a lot of tinkering and an argument why you want to have access up front, because basically you want to control the access really carefully. But typically, I don't create access using figure. I typically create them together using PLT subplots. But at the end of the day, that should be more or less the same thing. So you would start with PLT figure with some properties, and then get the access from that as you do in the code which you show. So that's another option to do it. The purpose is more control. And here I exercise a lot of control over the things I do. For instance, I set the while limits, etc., as you can see. So it's quite a lot of stuff. If you wonder what's here, basically this is how fast your supercomputer drops in an international ranking. So that's a lot of money which slowly goes through the drain. Actually, this is a nice plot. I completely forgot I had it. Anyway, so that's an example. You would also need subplots if you want to get multiple plots next to one another or in a grid of plots with matplotlib. Then you also need that subplots thing, but then you would have to specify the number of rows and the number of columns, the plots which you would have, and you would get an array of axes, and those would allow you to then plot two specific subplots. So that's another reason why you want access up front. I'm not sure that I have an example of that, but we can try. So figure axis PLT subplots and it's plural. I think it's n rows. Yeah, it's n rows. Okay, let's say one row will do. And L goals is 2. Okay. As you can see, now I get two plots next to one another and they're empty. So now I can add something to the first axis, so that would be the left plot, and I can do a plot of x and y. Normally that should work. Yes, it does. So I could now, to the right, plot of x and do computation directly. Yeah, the log is not a good idea. So let's say np log of 1 plus x. So diverge. Okay, and sorry, add that to the second pair of axes, so to the second plot. And now I've got my two plots next to one another. So that's another reason to have axes up front. So in this case, I have as many axes as I have subplots. And if this is a two-dimensional thing, so if I would have more than one row, then axis would be a list of lists. I think access is a list. Let's check. I don't know what type it is actually. It's not. Okay. So basically, this is the way to create multiple plots on the same thing. The matplotlib OX0 thing. Well, basically, all these commands return something. And in this case, it would be a line 2D thing. So basically, it's the result of the plot. So that's an object. So what I typically do is I put a semicolon after the last statement when I'm plotting stuff, because I don't want to see this. This is actually a representation of what is returned by the plot function. And that's not something I can do anything with, and I certainly don't want to see it. So typically I suppress output by adding a semicolon there. But it is in fact the address of that object which is returned by the plot function. So I could assign it to something and then do something with it. So basically it's probably a list, in fact, what is returned. So let's have a look what it is. Access, no, let me assign that to something A, and then do a type of A. And you see indeed it's a list. And if I check what type the first argument is, then it is a line 2D thing, which is basically some representation of this particular plot. Okay. But in general, I don't want to see it, and typically I put a semicolon there so that I get rid of that output. Okay. So you can do heat maps. So I have a function which returns 2D array at the end of the day, and I create some data. Notice there's mesh grid here, so that's the same thing as you're used to in MATLAB. That allows you to go from 2 vectors to two matrices, so that I can feed them as arguments to my function. So this is a 2-dimensional array which contains all the x coordinates. That's a 2-dimensional array which contains all the y coordinates. And z is going to be a 2-dimensional array which contains the value at the x and y coordinates. So that's a typical thing you do if you have x, y coordinates. You want to feed it to a function that expects x and y coordinates. Okay. Plotting a heat map, you can just do that with image show, imshow. You can also use mshow for matrix show. That's basically up to you. Typically I use imshow, and then I can specify an extent, so an x minimum, x maximum, etc., etc. And I can switch on grid lines if I want to. And that's what I get, and it's really, really ugly. So high values are in dark red, very low values are in dark blue, and yellowish greenish is somewhere in the middle. And personally, I get a migraine looking at this. So the default color map is, in my opinion, pretty crappy. So you can change the color map and actually look into Brewer schemes, because I'll give you a reference at the end of this section, because that gives you some idea about which color maps to use to display your data in a more convenient way. You can do 3D surface plots. Well, okay, let's not dwell. So here I used a different color scheme. So this is blue-red, and basically it also displays very low values in dark blue, very high values in dark red, but in the middle it's actually grayish white, light red, bright blue, and so on. And this is a color scheme which is very useful if you want to spot outliers. So here's a little bit abused, because for surface plot I typically don't want that, but for a heat map it can be very useful, because if you use this color scheme with a heat map, you'll immediately see outliers. So that's what it's very useful for. If you want to know more about that, have a look at Color Brewer 2.0. that gives you advice on choosing appropriate color maps. So that's just a web application. What is also quite useful is Coblis, and that's actually a simulator for color blindness, because it's a nice thing to take into account that some people have issues with colors. So you can simply take a picture and upload it to this particular web application, and it will render it as seen by someone with a type of color blindness which you can specify. So that's always useful if you create a plot and you think, well, okay, how is someone with visual problems going to perceive this? Then just run it through this and you will see what they get. So we had that, for instance, I had an endless discussion with someone who was doing data visualization during the COVID period, and he really insisted to have low levels of COVID infection in a spatial map rendered in green and high values in red. I told him, okay, this is nice, but someone who is colorblind is going to see gray, gray, and more gray. That person is not going to distinguish between low and high because it's green and red, and that person doesn't see a difference. Okay, endless discussion. But yeah, we are talking about 10% of the population, of the male population. So basically, it's a lot of people. So it's something to take into account. There are very many data visualization libraries for Python. So this is a website which shows quite a number of different plots, and then shows you in which Python library there is an implementation of that. So a few which I like are Bokeh, which I already showed you in the notebook. I like Matplotlib for silly things, I mean for very basic plotting. Bokeh for somewhat more interactive plotting. If you're into statistics, you certainly want to have a look at Seaborn. It's a very nice library for statistics, and I'll talk about it in Python for data science next week. There are others. I'll also maybe mention Altair as an alternative. Maybe I'll mention it, maybe not next week. I'll see. Don't know whether I get around to it. Okay, so basically this was very short about plotting. Okay, so let's have a look at the table of contents, because as usual some choices will have to be made. There are a few sections which we didn't discuss yet. So there is a section on Bokeh. I already showed you a little bit about it, but that section is mostly about doing really interactive plots where you can really do cool things. There is also a section on SymPy. You already got a little bit of SymPy when we computed the Jacobian of the projectile differential equation, motion, right-hand side thing. There is a section on HDF5. I already mentioned HDF5 when we talked about binary files. So HDF5 are an intelligent way of storing binary data. And there's also a short section about image processing and video processing in Scikit-Image and OpenCV. We can't do all four. So my suggestion is that each of you type your preference in the chat, so your top 2, and then we'll rank, and of course we'll deal with the winner, and then we go down. So just put your top 2 in the chat, and we'll decide from there. So SymPy, symbolic programming, symbolic computing, HDF5 binary file formats done right, image processing, video processing, and Bokeh. I can make a poll, but the problem is that you can only do top 1 then. So that will be a bit difficult to determine which is your number 2. But okay, I can do a poll if you want. We can try it that way. Okay. Multiple choice. Okay. So just going to call this. It's 3 numbers. Oh, that's cute. So preference. And let's see. The first one was SymPy. The second one is HDF5. Third one is okay. Okay, let's try. Okay, so that's plotting, and the fourth one is image plus video processing is garbage. So we eliminate that and we start the plot. The poll. Until now we have a tie. We remain having ties. Okay. I'd say that SymPy is the least popular. So if you want SymPy, now's the time to vote. But Bokeh and HDF5 are winners, and image processing and SymPy are less popular. Okay, so let's make sure that we talk about HDF5 and Bokeh, and then we can have a brief look at image and video processing, because it's not that much, and SymPy, I have a few. I'll just mention an example which is kind of cute. Okay, let's stop the poll. Frankly, this is not really unexpected, because that's what usually comes out. Why do I still do these polls? Anyway, let's go to HDF5 first, and then Bokeh second. So, HDF5 is a very nice file format. The nice thing, it allows you to store binary data, which is typically a bit of a pain, because if you have a binary file, you cannot read it yourself. You can't. Yeah, you can open it in an editor, but that's going to be very uninteresting. So basically, with HDF5, you have a much easier way to store binary data. And I'll show you some examples in a minute. So the name itself is derived from hierarchical data format, and that's already interesting because we apparently can have a hierarchy here. So what is meant by that? I'll explain in a minute. One of the big selling points, let me just switch back to the chat just to make sure that if there is a comment or question that I can see it. So one of the big selling points of HDF5 is that it is system independent. It's operating system independent. It's even programming language independent. And it basically allows you a way to store data in such a way that you can read it anywhere, regardless of where it has been written. So that is a big selling point. And it means that I can save my data in HDF5 from a C++ application and do my post-processing in a Python application reading that same HDF5 file. So that is really convenient. But it doesn't end there. So the hierarchical thing is basically that you have an abstract data model. So at the top level, of course, you have a file. That's pretty obvious, an HDF5 file. But in that file, you can have groups. And in fact, there is a one-to-one correspondence with your file system. So you can view a group as a directory. So in a file, you can have groups, you can have data sets. Data sets can either be directly in a file or they can be part of a group. And that's, of course, where the hierarchy thing comes from, because a file basically corresponds to the file system on your computer in a way, conceptually. A group corresponds to a directory, and the data set corresponds to a file. So since I can have data sets in a group, I can have groups in groups, etc., etc. I can organize my data hierarchically within one file. And that's kind of convenient. Then, of course, there is something very important, and that is that the data set, that's the actual numbers, the actual data you're storing in that file, actually have a documented type. So in the file, in the HDF5 file, for each data set, there is stored what type of data that is, whether it's an integer, whether it is a 8-bit integer, or an unsigned 64-bit integer, or whatever, or floating point number. So that data is part of your file. And you can also annotate your data sets, also your groups, with attributes. And those you can pick. For instance, you can say, okay, I have a data set, and that data set represents measurements of or simulations of a magnetic field in 3 dimensions. Okay, the unit of that thing is in fact millitesla. And you can annotate your data set with these units. And what you provide as metadata is entirely up to you. You can pick that, it doesn't matter. Okay, so that's actually very nice. So basically your binary data is documented. For instance, if you have a data set and that represents a 3-dimensional array, that information is part of your file. If that array contains single precision floating point numbers, that is part of your file. If that these floating point numbers were encoded in little endian, that is part of your file. So all the information which you need to correctly interpret the types of your data, the data space of your data, so basically the layout of your data, is all stored within the file itself. And that's, of course, quite a cool thing. Besides that, you can have extra attributes at the level of groups, data sets, files, and so on. Okay, so that's really, really cool. Okay, so that's the abstract data model. You also have a storage model. So data is typically stored in n-dimensional arrays, and there is somewhere an upper limit, but it's pretty high. I think you can store up to 17-dimensional arrays, something like that. I don't quite recall how much it is, but it's pretty high. So the data space, as I mentioned, describes the layout. So that means the rank and the dimensions for such arrays. And there is also type information, and that describes the type of a single data element. So elements in such a data set can be atomic, so an integer, a float, a string, a time, but they can also be opaque. And this you can use, for instance, to create a dataset containing JPEG images. Those are just an opaque blob of bits, but they can be stored in such a dataset as well. They can also be compound, or composite rather. So you have compound, which is basically similar to a struct in C, or a tuple in Python. You can have an enumeration. This is typically something you want if the number of things you are enumerating is pretty low, then let's say space. It can also be an array, and it can be variable length, which is also convenient. You can create a data set and later on add rows to it, or add 2-dimensional slices to it. That's all possible. Okay, so basically the important thing here is it's self-documenting and it's discoverable. So you can give me an arbitrary HDF5 file and I can figure out what's in there. Give me an arbitrary binary file and maybe with a lot of work I can figure out what's in there, but likely not. So that's the key distinction. And of course, nowadays HDF5 is really, really popular because the machine learning people have taken it up as their preferred way to store models, as their preferred way to store evaluations of models and so on. So that's actually a very nice thing. Also, a very nice feature is that you can do partial read and write. So if I have a data set, which is, for instance, a 3D array, I don't have to read or write that entire array. I can read or write a slice of it. And in HDF5 parlance, that's a hyperslab. So that is also very convenient. So there is also the storage model. You have some filtering, which means that you can automatically compress your data. Whether you should do that is maybe up to you. Of course, this will cost you performance. Your I/O will be slower. There's also error detection, so you can switch that on, and then if a bit is changed in your data, you will know it. You won't know what was changed, but you will know that something's changed. So sometimes, for some applications, that might be convenient. So as I mentioned, data sets can be extended, so that's cool. And you can have storage drivers. So you can have a single file, which is the usual. You can have multiple files. You can have multiple files on parallel file systems. So that can sometimes be convenient. If you don't really have a parallel file system, you can opt for multiple files and still pretend that it's parallel. But you can also have them in memory. I would say typical usage is single file. Okay. You can use HDF5 from C, C++, from Fortran 90, from Java, from Python. And in Python, you've got two choices, two implementations. One is PyTables and the other is H5Py. When I first created these slides, I used PyTables because it was, at that time, more mature, in my opinion, than H5Py. Nowadays, H5Py is actually quite a bit faster for a number of operations than PyTables is. So that's why I switched to H5Py as my default HDF5 library in Python. But slides are still available for both. So depending on what you do, you might prefer PyTables or H5Py. The nice thing, of course, is that HDF5 files can be read by any program in any language. And that's really, really cool. Also, MATLAB, for instance, can read HDF5, R can read HDF5, etc., etc. So that's pretty cool. So if you want to do certain things in C, C++, and Fortran, that's not really so easy. But in Python, it's really, really trivial. So that's actually a big benefit in Python. Okay, so the first thing, of course, is to import the appropriate modules. And in this case, import H5Py. And of course, we will also need NumPy typically. Okay, so opening and closing an H5 file, very easy. That's H5Py file. And in this case, I open it for writing. So the mode is write. And that's the file name. No surprises here. Okay, open for modification. So to extend a dataset or to alter a dataset, which is stored in the file. A for append, so that's open for modification. And for read, pretty obvious, R. Okay. Closing a file, just call the close method on the file handle. Or, better, use a context manager. So with H5Py file, then of course, if something goes wrong in in the body of your WIT, the file will be closed appropriately. It will anyway be closed at the end of this block. So that's, of course, the preferred way of dealing with many things in Python, just using context managers so that you don't have to worry yourself. Okay, creating a group, so a subdirectory is pretty straightforward. You've got your file handle H5 file, and you just use create group, and you give it a name. Okay, so this will create a group at the top level of your H5 file. So it will be a subdirectory in a way of your file. Okay, so that's easy. Creating a subgroup. So essentially here, now I'm creating a group inside of this group. So that will be a subgroup. So in input, there will be another group which is called fields. So that's quite convenient. I can do that in a different way. And here we have create group /input/fields. And of course, given this notation, it's pretty obvious where the analogy between a Linux file system and groups comes from in HDF5. It's the exact same notation. Okay, now let's add a data set. So I'm creating a data set here, which is basically just a NumPy array. I do some sophisticated manipulations here. I use mesh grid, blah, blah, blah. I've got my magnetic field. Okay, great. And I'm going to add that to the HDF5 file. So in my fields group, I'm going to create a data set. The name of the data set is magnetic, and I specify the shape, and I specify the D type. Okay, and then I can populate the field, and I'm just copying, in this case, all the rows and all the columns of my NumPy array into my field using array slicing. Very convenient. And then you see there's an H5 file flush here. So basically, the HDF5 library has the option not to immediately store data in the file. It can keep it in memory for a while in order to do stores more efficiently. So if I do a flush, I'm telling the HDF5 library, okay, write it to the file now. That's the idea. That's very similar to your typical flush operation, which you have in I/O statements, for instance, in Python. There you also have the flush in order to kindly ask the operating system to actually write it to the file as you would like it to do. Here in the HDF5 library, it's really going to do it. There is no option, it's really going to write it. Okay. So basically, where you add or where you create the data set depends on what you apply the create dataset method to. In this case, the dataset magnetic would be created in the group, in the fields group, which is into the, I don't remember, input group. Okay. What else? Yes, one of the things to note, of course, is that types in H5Py are the exact same as in NumPy. So that's why I get away with using the D type argument of the field's values, which is a NumPy array. Okay, adding a two-dimensional array. Here's another example. So I create my NumPy array, and then I just add the array to in this case, directly in the H5 file. So not in a group, but directly in the H5 file. And as you can see, again, I copy my data and I flush. Easy. Okay, so I mentioned that you can have custom annotations. And for instance, to the magnetic field, so the data set with name magnetic, I can add attributes. So in this case, I have the attribute units, and I set that to millitesla. And this is arbitrary, so I can pick any key I want and give it any value I want. So that's for human consumption. The systems themselves typically don't do anything with that, but that allows you to annotate your data. And of course, that's nice because it means that you can avoid unpleasantness such as trying to land a Mars lander 200 meters below the surface because you actually confused feet and meters. It happens. Okay, so I can pick any attribute name which I want, and I can also give attributes to groups, so to directories. Okay, and of course it might make sense that I don't want to modify that, whatever. Okay, so basically they behave like Python dictionaries. So to set and to get to remove annotations, it's all more or less the same. And you can also iterate over attribute names. So you have a key method, and that will give you the names of all the attributes of the field group in this particular case. Okay, so now let's read some stuff. So I open, of course, my file for reading, and then I can just get the magnetic field by specifying the path to my dataset. So that was in a group called input, then a subgroup called fields, and then a dataset which was called magnetic. Very easy. And then I can print the average of the magnetic field if I want. Okay, now I mentioned hyperslaps, and if you want to do that in C++ or in Fortran, whoa, okay, that's a few pages of code. In Python, this is really, really trivial. So in this particular case, I'm going to read in an array, which is just an array with a number of rows and 2 columns. They or 3 columns, depending on whether this is 2 or 3 dimensional. So it's just let's say the it represents the coordinates of particles, whatever. So in this case, what I want is going from the 4th up to the 7th particle, and I want both x, y, and whatever, maybe z coordinate. So I just use array slicing in order to do a specific read into a certain data set. And this is syntactically not correct because this square bracket is not closed, and also my string is not closed. So this is not entirely okay. So there should be a closing quote and a closing square bracket. So here the H5Py is going to do the right thing. It's not going to first read the entire array of positions. It's just going to be going to read the rows and columns which I specify. Notation is just Python slicing as usual. So very easy. I'm just going to read the coordinates of 4 particles. Okay, I can even read non-consecutive data. So here I'm specifying the 3rd, the 5th, and the 7th row, and I'm only going to use to read those particles on those rows. And again, I want the x and y coordinate. Okay, so hyperslaps, trivial, both for read and for write. It's of course the same for read. Here it's okay. So indeed, here's something missing. Okay, so that's pretty cool. On the command line, you have quite a number of helper applications, for instance, h5dump. And that allows you to print a textual representation of an HDF5 file. So that's very convenient because if you're starting to develop with HDF5, it's not always that easy, and things might end up in wrong places. You might not have the type you expect, whatnot. And then basically, if you have a small file, you can just use h5dump. You can see what it looks like, and you can correct your mistakes or be reassured that what you're doing is the right thing, and so on. Of course, if you have a 100 gigabyte HDF5 file, maybe you shouldn't use h5dump because that will take forever to get a textual representation from. So don't do that. That's not a good idea. You also have h5ls, and you probably can guess what that does. It's similar to the ls command in Linux, so it shows you the content of something. And of course, given that there is a strong correspondence between an HDF5 file and the file system, ls will give you the content of a file or the content of a group, a subgroup, and so on. So that's convenient. You also have h5 copy, so I can copy a data set from one HDF5 file into another, which can also be convenient at times. I can create a new group in an existing file using the h5mk group. Similarity to mkdir is, of course, not a coincidence, into an HDF5 file. And then if you want to create C++, C, C++, and Fortran applications that use HDF5, then it's convenient to use the wrapper, the wrapper sort of compilers in order to build your code. Maybe the most interesting purpose for Python programmers is to use the show config option, because that shows you how the HDF5 library has been built, and that has some impact on some features. So that's why that is convenient. Okay, so same story, but for the PyTables. So I'm going to skip this. If you prefer PyTables, just have a look at the slides. It's actually just the same thing, but now with a different Python implementation to read, and it's very similar. So this is the only difference I'm aware of. You have tables, the concept of a table, and this is something which, as far as I know, you don't have in H5Py. On the other hand, do you want to use it? I don't know. But this is a little bit like data frames in Pandas, but then done in HDF5 files. So is this useful? Maybe, maybe not. Probably not to deal with it directly. If you want this type of thing, yeah, use Pandas. I mean, that would be my advice. Okay, so let's skip this. Any questions about HDF5? All right, I consider HDF5 a very good thing. In case you're into climate research, in case you're into any type of research where you typically deal with spherical coordinates, you might actually want to have a look at NetCDF rather than HDF5. So NetCDF is built on top of HDF5, so you get all the advantage of HDF5, but it has some additional machinery in order to conveniently deal with spherical coordinates and cylindrical coordinates and so on. You can do that in HDF5, but it's a pain, while in NetCDF it's very natural. So if you're interested, there is example code how to deal with NetCDF files from within Python. That's in the repository. Okay, so let's talk about Bokeh. Bokeh is pretty neat. It's also a plotting library. It's easy to use. The nice thing, it integrates nicely with Pandas, and it's very cool for interactive stuff in Jupyter Notebooks. And what's also very nice, you can export to an HTML page, and you still get interactive plots. Why? Because the interactivity is in fact a JavaScript thing. And of course, if your HTML page just loads the appropriate JavaScript model, you're set. So that's a big convenience. A disadvantage is that there is no reasonable way to get LaTeX labels. So that's unfortunate. Maybe they'll add that at some point, but I'm not aware that that has been done. So I would say in a way that it's a little more oriented towards information visualization rather than scientific visualization, but okay. I mean, you can use it for scientific visualization. You've seen what I did with it in the notebook on the projectile firing. So basically, it's kind of cool for that. Okay, let's see whether I have a notebook, because it's a little more interesting than looking at slides. And that should be a nice one. Okay, so let me... we import quite a lot. As you can see from Bokeh, there are 4 lines of stuff which I'm importing, so quite a lot of things. Let me just load that, and as you can see, it gives some feedback. It says that this is successfully loaded. I think this is a fairly old version, so I'd have to update my environment at some point. Anyway, So I'm going to implement the function. This you recognize. This is the right-hand side function of my set of differential equations. And basically, y1 is the velocity, the angular velocity. Y0 is the angle of a pendulum which is subject to gravity on the one hand, to friction on the other hand, and to an external force here. Okay. So I have quite a number of parameters. I need to compute the Jacobian. Well, that's all straightforward. And then function to solve that set of differential equations. Someone has activated his microphone. Do you want to ask a question, or is that by accident? That was likely by accident. Okay. So I define a function to solve that set of differential equations for given initial conditions of the angle, the angular velocity, and for given values of the parameters. I also specify some tolerances and so on. And of course, my usual suspects, the right-hand side of my equation, the Jacobian, and the maximum time interval. And here, this is just again SciPy. So I imported ODE from SciPy integrate. And here I'm just creating my integrator. Okay. So that's just the function definition. And now things get a little more interesting. So of course I can create my data, and that's just solving that set of equations, done very fast. Now I can create plots. So I have plot options. I set the width and the height of my plot, and I set the tools which I want. So I want to pan, I want wheel zoom, and I want help as tools. Okay. Then I create a figure, and I use the plot options for that. And I also get the axis now. So basically I can set the x-axis label to t. Okay. Then the y-axis label I set to theta. So that will be the angle which my pendulum makes. And then I can create a theta plot just by, on the figure thing, calling the line method. So this is going to be a line plot. And I'll specify the x and the y values. And those are just values in data, nothing special. Then I also have the omega figure. So that will give my angular velocity as a function of time. And again, I'm creating a new figure, same options actually. But as x range and y range, I take the values of the theta figure. So the omega figure and the theta figure will share the x range, and they will also share the y range. Okay. And then I fill with the axis of the omega plot, and I create the omega plot. Of course, I will plot angular velocity versus time, and again, it's a line plot. And then I create a third plot, which is the phase space plot. So basically, again, very similar thing, but in this case, I'm going to plot theta versus, well, omega versus theta. Okay, so I've created 3 plots, nothing has happened yet. And then I'm going to call a grid plot, where I actually have the theta figure next to the omega figure in the first row. Then in the second row, I have nothing, and then the phase figure. So if I do that, not options. Okay, I would hope that this does something, but nothing much is happening. Okay, that's somewhat inconvenient and somewhat unexpected. I don't get an error and I don't get a plot. I might have to initialize plotting. Yeah, I have output notebook, so that should be okay. This is weird. I do have an internet connection, so okay. Okay, right. I was already thinking that I missed the plot show, but I first want to do something else. And that's why it's not there. So I want to create an update function. And this function would be called anytime I change something. So basically it will recompute the data and then push that to the notebook. So basically I'll push the changes which I make to my plots to the notebook. The changes I make are the data source, which I would do by recomputing the function. So I call the solve function again. But this is just a function. Okay. And now I'm going to do show plot with a handle. Okay. So these are my plots, and indeed you recognize that this is the theta plot, the omega plot, the phase plot. This is with no friction, with no driving force. So indeed, in the phase space, you would expect an ellipse. Okay, so that's exactly what we get. But now things get interesting, because now I can add this interactive thing. And that gives me sliders for each of the quantities of interest. So as you can see, the default for Q, that is the damping factor, is actually 0. I'm going to decrease the size of this notebook a bit, so that I can get more on the same page. Okay. And now I'm going to change this. So I'm going to change Q. And with some luck, which doesn't seem to happen. Come on, move it. So what ought to happen, but what doesn't seem to happen, is that since I change the values, I have my update function here, so that should actually change my plot. But it doesn't seem to happen for some reason. That is very annoying. Okay. Normally this should change interactively, so I don't know why this is not happening now. Show is okay. Notebook handle is true. Okay, I don't know. This is weird. Yeah, normally this should be interactive. So if I increase Q, you should see that this is going to be a spiral, that that the amplitude is going to decrease over time. But yeah, that is not happening for some reason. That's a little bit a problem with using Bokeh in Jupyter Notebooks. Most likely I need to install some extension here. Let me see. I have nothing installed at all. Okay, and I probably need PyWidgets. Which does not exist. No, this is not what I want. That's not what I want. No, I should do that differently. So apparently I don't have, I recreated this environment, and most likely that is not part of my environment definition, which is why it was not recreated. So I'd have to look up how to do this. But there is likely just something missing in my current installation of Jupyter Notebooks. But the cute thing is, if this were to work, hallelujah, then if I were to change these sliders here, then all three of my plots would be updated automatically. So that's kind of cute. So you can do other things, but this is also likely not to work. So let's see. Yeah, this might actually work. Let's see. So in this case, I have two plots which are kind of connected together. And now I can, in fact, select some points. So for instance, I'm going to select here the first few points in this plot. Okay, I would like the cursor to change, but apparently it doesn't. So if I select these points, then again, absolutely nothing is happening, which is, wait, this was not selected. So let's, okay, now might be better. Yeah, so that works. Okay, and now you see that in the other plots, also the corresponding points are selected. So let's do that again and take something which is even less. So suppose I'm interested only in the first iteration, well, so in the first oscillation of my system, something like that. And then you see that indeed, here in my phase plot, I'm starting out here and I'm going here. See? So this is a nice way to limit what you see by just selecting it. So that's kind of interesting. Now I should have added the reset thing because this is not going to be interesting. And I can do this anywhere. So I can say, okay, this part here, okay, now these are the corresponding positions, the angles, and these are the corresponding velocities. So I can do that wherever I want, for instance, this part here, and then I get these points and so on. So that's actually rather nice. What you can also do is, and how do you do that, by the way? Basically, what you do is you connect the plots. So I have a theta plot and I have omega plot and a phase plot like before. Then I have my grid plot, but I'm actually connecting them together somewhere, and that is here. As you can see, as source, I have a point source, and it's always the same point source. And this point source I have created here, and that is a column data source, and that is based on the data, and that basically means that I can actually do this selection thing. So that's thanks to the point source here, which I parse as a source to the circle method in this case, because I want a scatter plot rather than a line plot. The plot options, what do we have? As you can see, I have the plot options here. A reset would be a nice idea to add. Basically, apart from that, there is nothing special happening here. Okay, last type of plot. Let me perhaps increase the font size again. So basically, now I'm adding a hover tool. So let me just do it and show you. It's the easiest thing. So basically, if I hover over a point, I actually get annotation. So I get the time, the theta value and the omega value for this particular point. Of course, the theta and the omega value is not so interesting, but for this plot, of course, I don't have time information. So I don't know at which point in time of the run of my, well, of the oscillations, this was actually computed. So I can have a look here. Well, this is at time, if I can manage, time, well, 0.5 seconds. This one is at 1.5 seconds, and so on and so on. So this makes it easy to explore my data. I do that by creating a hover tool. I create tooltips, and this is a particular format, but basically it means these are my labels, and then I get inserted automatically the value of the time for that point, the theta value of the time for that point, and the omega value of that point. And then I add, as tools, I also add the hover tool. Okay. And then I just plot and I get this. So this is very convenient. And if you have the widgets thing installed in Jupyter Notebook, then this thing should actually also work, which now unfortunately it doesn't, which is a bit annoying. Here's, whoa, lots of stuff. There's something else wrong. Ooh. That is the problem. There is some bug somewhere. That is the actual problem. See? Yeah, so there is a discrepancy between my X values and my Y values for some reason. And that is the actual problem. So there is a bug here somewhere, and I'm guessing it is because I did this multiple times, and there is a variable which is leaking somewhere. I think that that's the issue, but I'd have to look into it because this is, of course, pretty silly, and I'd have to look what's going on. Probably here there is a leak of something. I'd have to look. But yeah, it's a bug. It's not due to the widget thing. And now, whoa. Now actually something happened. Okay, cool. Why is not clear, but okay, now I don't know why it. But this will be just the initial thing, and then it goes wrong. So there's something wrong in the update function. That is most likely the case. I'd have to look what it is. I don't know. Can't see it right now. But there must be a bug somewhere. Anyway, so that was a little bit about Bokeh, and I think that corresponds with what is in the slides. This is just the same plot as we did with Matplotlib, but now done with Bokeh. Essentially, very much the same thing, slightly different approach. You can also control line width, line dash, and so on. And the alpha value you should be able to specify that as well. Okay. You can also do this in an HTML file. Then you get a widget. You can change that. This plot changes and so on. So that's kind of cool. Don't forget you need working internet connection for that, because the JavaScript library is going to be downloaded as soon as you load the HTML page. So no internet connection, no interactive plot. Very easy. Okay, linked figures I talked about, blah, 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 linked brushing, hover plot, etc., etc. Okay, so we just have a very brief discussion of image and video processing, because that was the third most popular. I'll go pretty fast over that just to show you some options. Basically, what I'm going to talk about is scikit-image and OpenCV. So OpenCV for video processing rather than for image processing, but you can do image processing with OpenCV as well. Okay. So one of the things you might want to do is image restoration. This image is pretty blurry. Okay, I want it to be sharper. So what I can do is use an unsupervised reader method in order to create dynamically a filter which will make this more crisp, which will sharpen this. And for that you start from an initial pointer, from an initial filter, which is just, well, a uniform filter. And the unsupervised reader method will actually take these points as initial values and then create a filter which is better for this particular image. So that's kind of nice. And then an image is just a 3D NumPy array. So 2Ds for the pixels, and the third one is RGB, so red, green, blue. And then the result is this. Don't know whether you're able to see the difference, but for me, it's quite a lot more crisp. And this is more or less all the code, except for reading the image. Apart from that, that's all there is. So again, just like for signal processing, this is a really nice library to get rather sophisticated things done with very few lines of code. And what is really nice about it is that documentation is quite superb. So for each method which is implemented, each algorithm which is implemented, there is a reference to the original article which introduced that method. So you can go there, read, to see what the parameters are, how you can tune the method to work more appropriately for your problem, and so on. It also has a lot of I/O modules, so basically that's also pretty straightforward. Another example is segmentation. That's a very typical task in image processing. So I want to segment objects in my image file. And in this case, we start with an initial guess, and that's the circle. And what I want to do is I want to segment the head of the astronaut. I start with a circle around it, and then I use the active contour method on my initial snake. I have a few parameters which I can tune in order to see how tight this is going to be. And if I do that, this is what I get. So the red curve is in fact the segmentation. And as you can see, it's really, really good. We have a little bit too much here around the ear, but apart from that, the segmentation is really the head of the astronaut. And again, this is almost the entire code, except one thing which I did. I smoothed the original image a little bit. And that's something that you know to do when you read documentation of active contour. It's going to tell you, well, okay, this method is actually going to work better. If you smooth your original image a little bit, then you get a better segmentation. And smoothing is very easy. You can just use a Gaussian kernel. So this is a convolution with a Gaussian kernel. And in this case, I use a 3-pixel kernel. So again, just one line of code plus the import, and you're done. So that's pretty powerful. And again, what I like most is the references to the original research articles. Okay, a little bit about video processing. So that is also very easy using OpenCV. And I can define a capture device. So it's going to look for devices on your computer and see what can do video capturing. So in my case, at the moment, that would be my webcam on top of my monitor. So using that capture device, I go into an infinite loop, and I'm going to read from that capture device. That will give me two things. That will give me status and frame. And the frame is again a 3D array. But there is one specific thing. It's not RGB, it is RBG, if memory serves. So the color space is slightly different. It's not a problem, but you need to be aware of it. So if status is non-zero, then there is an issue. So do something. Otherwise, I can just display the image, and then you just see what the camera is capturing in real time. And if I press a key, so if I press the Q key, then we stop. So this is the end of my infinite loop here. Okay, then I have to destroy the windows. There will be a window popping up automatically due to the IM show. And I destroy that window, and I also release the capture device. Okay, so that's very easy. That's just essentially a recording program. Well, in this case, it just shows whatever the webcam is seeing. You can also save all these things to a file, maybe an HDF5 file, who knows, and then you have basically a recording of whatever you want to do. Okay, it's BGR, not, so we get the blues first, then green, then red, rather than RGB. So it's in just the opposite order. Okay. So I can write to a file, so that would be very easy. In that case, I have to have a writer, and this is a bit annoying. you need to get this right. And that's something you have to look up in the documentation. So this is XFIT format, but you have to specify this in a weird way, in the sense that you actually have to specify each character individually. So that is a little annoying, but okay. So not so very interesting, except for the video encoding thing. Then what I want to do, and I'll show you first the result and then how to do it. So what I want to do, I have the yellow ball and I want to follow it with the blue rectangle while it moves through the image. And as you can see, this happens quite well. So the blue rectangle really keeps track of the moving image. Here it briefly loses it, but it gets it again. Okay. So I'd say pretty impressive. The algorithm which is used here is the mean shift algorithm. So that's a certain algorithm, and just like scikit-image, OpenCV also has excellent documentation. So again, you're going to find a reference to the original mean shift, to the original article which introduced mean shift. And so this mean shift is actually going to produce a tracking window. So that's going to produce the blue rectangle here. And in order to use mean shift, we need a couple of things. So this is of course executed each time I capture a frame. And in this case, I'm going to capture from a file, but could capture in real time as well from from a video camera, whatever. And basically, what I'm doing here is interesting. I'm converting the color space. So you're familiar with red, green, blue color spaces, or in this case BGR, so blue, green, red. But there are different color spaces, and another one which is very convenient, especially in this particular case, it's HSV, so hue, saturation, and value. So the hue, in fact, is a single number that controls the color, and that's very convenient here, because I'm changing my image to that color, so from BGR to HSV, and then I'm going to select the color between the 0 and the max hue, and this I'm going to set. And that is actually going to tell the mean shift algorithm, well, not the mean shift algorithm, but that is actually going to select parts of the file based on this particular color. And that's the back projection algorithm, which is a different algorithm in OpenCV. So that is based on the HSV image and on the hue which I'm interested in. For that, I need a histogram, and that's something which I computed here. So this is going to create a hue histogram of the region of interest. And that's happening in this particular case. So that will be computed for each frame as well. And then I'm using that as input to the mean shift algorithm, and it's going to follow the ball all the way. So again, this is the entire code. So this here and that, and maybe something to open a file, whatever. But basically that's it. So 30 lines of code, and you've got the whole thing. And again, I really don't know anything about video processing. So at the time when I wrote the slides, I also went into all the details, looked at what the back projection was doing, how the mean shift algorithm worked, and so on and so on. And that took me something like, altogether, including getting to know all the stuff, again, 3 hours. So that was really, really fast. Okay. So basically, you need to understand the algorithms. That's very important. But the big advantage of scikit-image as well as OpenCV is that you actually get references to very good material. There is a lot to explore, so basically check out the documentation. It's your best source of information. Okay. Any questions? Because we'll conclude. We've already run 10 minutes over time, so we'll conclude here. If there are any questions, I'm happy to try and answer them. If not, I wish you a very pleasant remainder of the day, and I hope you enjoyed the training. Yes, please do. Okay. Showed some references for NumPy. Yeah. A book I'd recommend. There are probably quite a number of books, but I really can't recommend one because, to be honest, most of what I learned about NumPy, SciPy, and so on, I just learned from documentation. So, to be honest, I'm not aware of a good book. There must be books, but no, I don't know them. I never use them. Certification, yes, but that's done by the Secretary's Office. The video recording is available upon request. I'll download it and upload it to YouTube. It will be unlisted, but if you want it, just send me an email and I'll send you a link. That takes a while because it will. Yeah, I know documentation is indeed quite dry. I realize. The problem is you need to know your numeric methods, and then you have something. Then you will learn something from the documentation. If you don't know the algorithms, the documentation of NumPy and SciPy is not particularly useful. That's definitely true. So the slides are available on GitHub, so I don't need to send them. But what I will do is I'll post the link to the GitHub repository again in the chat, because if you were joining later, then you didn't see that in the chat. So let me do that again. So this is the repository. So there is on the one hand the slides, which I showed, and on the other hand also all the code. And much more, because, for instance, there is a section in the repository on NetCDF, which I just briefly mentioned. There is also a cool part about X-array, which I didn't mention at all. There are nice examples, some interesting SciPy examples, also some stuff. That's not yet in the master branch, apparently, but also some stuff about very nice visualizations of simulations, but those are only in development branch, I think. Yeah, the VPython thing is indeed in the development branch and not in the master branch yet. So there is quite a lot of stuff there in addition to what we have been discussing. With respect to the videos, just send me an email. It will take a while because it takes a while before Blackboard or Toledo, whatever you want to call it, has processed the video. Then I need to download it. I need to upload it to YouTube, and YouTube also takes a while to process it. So by this evening it will be there, but not earlier. Any other questions? If not, thanks for participating, and perhaps see you at another training. Yeah, my videos are on YouTube, but they're unlisted. I can't make them public except to participants because of GDPR considerations. The problem is your names are visible, and I don't have your permission to make them publicly available. And that's why I can't make these videos public, but I can, of course, send the link to participants. This I'm allowed to do. It's annoying, but that's live.